October 24th, 2025, 4:10 in the morning, Universal Time. While most of South Africa slept under a canopy of stars, 64 massive radio dishes stood awake in the Karoo desert, their surfaces tilted toward a patch of sky so close to the sun that observing it bordered on impossible. The MeerKAT Radio Telescope array, one of the most sensitive radio instruments humanity has ever built, was doing what it does best, listening to the whispers of the cosmos. And on that particular morning it heard something that had never been detected before in the entire history of astronomy. 2 absorption lines appeared in the data stream, faint yes, barely distinguishable from the background hiss of the universe. But they were there, structured and deliberate looking. The frequencies were precise, 1.665 GHz and 1.667 GHz. If you know anything about radio astronomy, those numbers should make your pulse quicken. They're the main lines of hydroxyl radicals, the OH molecule, a chemical signature that appears when water breaks apart under the harsh glare of ultraviolet light. This wasn't static. This wasn't interference from a passing satellite or a glitch in the equipment. This was chemistry broadcasting itself across hundreds of millions of kilometers of empty space. And it was coming from something that didn't belong to our solar system at all. The object in question had been designated 3us Atlas, catalogue number C2025N1. The I stood for interstellar, the third confirmed visitor from beyond the gravitational boundary of our Sun. It had been discovered earlier that year, racing inward on a hyperbolic trajectory that screamed outsider. Astronomers had been tracking it for months, watching it grow brighter as it approached perihelion, the point of closest approach to the Sun. They'd measured its speed, calculated its orbit, analysed its tail formation, documented its brightness variations, but nobody, not one person on Earth, had detected a radio signal from an interstellar object before, ever. In the entire history of radio astronomy, going back to the 1930s when Carl Jansky first detected radio waves from the Milky Way, this had never happened. 3I Atlas had just spoken to Earth for the first time, and what it said was written in the oldest language in the universe, water breaking apart under starlight. Let's rewind to July 1st, 2025. The Atlas Survey Telescope in Rio Hurtado, Chile, part of NASA's Asteroid Terrestrial Impact Last Alert system, was doing its nightly scan of the sky. Atlas is designed to catch asteroids and comets that might pose a threat to Earth, systematically photographing huge swaths of sky several times each night, looking for anything that moves against the background stars. That night something moved. Something faint, travelling at extraordinary speed through the constellation Sagittarius at about 61 kilometers per second relative to the Sun. The automated detection software flagged it immediately. Within hours, astronomers around the world were turning their telescopes toward this mysterious visitor, trying to figure out what exactly they were looking at. Pre-discovery observations were quickly pulled from archives. The Zwicky Transient Facility had actually captured images of it dating back to June 14th, but the object had been so faint and was passing in front of the dense star fields of the galactic centre, making it nearly impossible to spot against that crowded background. Amateur astronomer Sam Dean later noted Atlas observations going back to June 5th, showing that this visitor had been in our solar system for weeks before anyone noticed. But what was it? Initial observations were unclear. Various astronomers, including the respected comet hunter Alan Hale, reported no cometary features at first. It looked like it might be an asteroid, just a bare rock tumbling through space. But on July 2nd, everything changed. 3 different observatories, the Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope at Mauna Kea, all observed a marginal coma with a potential tail-like elongation. It was active, it was outgassing, it was a comet. More importantly, when astronomers calculated its orbit, they found something extraordinary. The trajectory was hyperbolic. This object wasn't in a closed orbit around the Sun. It was moving far too fast to be captured by our star's gravity. It was passing through, travelling at roughly 221,000 kilometers per hour, or 61 kilometers per second. That's escape velocity and then some. On July 2nd, the Minor Planet Center made the announcement official, giving it the designation 3 Atlas. The 3I signified that this was the third confirmed interstellar object ever discovered, The first was One-Eye Oumuamua in 2017, that strange, elongated object that accelerated inexplicably and showed no signs of cometary activity. The second was Tui Borisov in 2019, which behaved exactly like a normal comet, complete with a beautiful tail and predictable outgassing. 3i Atlas was something in between. It had cometary activity, yes, but from the very beginning there were anomalies, things that didn't quite fit the standard model. Let's be absolutely clear about what interstellar means in this context. 3i Atlas didn't form in our solar system. It formed somewhere else, orbiting a star we'll probably never identify, in a planetary system that might be thousands of light years away. 4.6 billion years ago, give or take, when our sun and planets were still coalescing from a cloud of gas and dust, 3i Atlas was forming in an entirely different stellar nursery. At some point in its history, something ejected it. Maybe a close encounter with a giant planet in its home system flung it outward with enough velocity to escape that star's gravity. Maybe its star system went through a period of violent instability, with planets migrating and scattering smaller bodies into interstellar space. Or maybe, as some have speculated, it was deliberately sent. But we're getting ahead of ourselves. For millions of years, perhaps billions, 3i Atlas drifted through the cold darkness between the stars. The temperature out there is just a few degrees above absolute zero. Cosmic rays bombard anything in their path. Occasionally it might have passed through interstellar clouds of gas and dust, accumulating a thin coating of material, but mostly it just drifted, frozen and dormant, carrying whatever ice and organic compounds formed on its surface in that distant protoplanetary disk. Until it encountered our sun's gravity well. Slowly at first, then faster and faster, it fell inward, accelerating as it plunged toward the warmth and light it hadn't felt in eons. By the time astronomers discovered it in July, it was already inside the orbit of Jupiter, travelling at speeds that native solar system comets rarely achieve. The orbit they calculated told a stark story. Perihelion, the closest approach to the Sun, would occur on October 30th at a distance of about 1.4 astronomical units, or roughly 210 million kilometres, just inside the orbit of Mars. After that brief encounter with our star, 3i Atlas would swing back out into space, travelling even faster than it arrived, eventually reaching a velocity of over 40 kilometres per second as it left our solar system behind forever. This is a once-in-a-lifetime visitor. It will never return. Its hyperbolic trajectory ensures that once it leaves, it's gone for good, headed back into the vast darkness between the stars, carrying with it whatever secrets it holds about that distant planetary system where it was born. To truly appreciate what makes 3i Atlas special, we need to understand the other two interstellar visitors we've confirmed. Each one has been completely different from the others, challenging our understanding of what these cosmic wanderers actually are, and teaching us that the diversity of objects in the galaxy far exceeds what we see in our own solar system. Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii, was the first confirmed interstellar object humanity ever detected, and it was bizarre from the start. The name, chosen from Hawaiian language, means scout, or messenger from afar, reflecting the object's role as humanity's first direct contact with material from another star system. Initial observations suggested it was highly elongated, perhaps 10 times longer than it was wide, tumbling end over end as it raced through the inner solar system at over 87,000 kilometers per hour. Some calculations suggested it might be shaped like a pancake, roughly disc-like, while others favoured a cigar shape. The truth is, we never got close enough or collected enough data to definitively determine its geometry. What we could see was that it was small, probably no more than a few hundred meters across in its longest dimension, and that it tumbled with a rotation period of around 7 to 8 hours. But the truly weird thing about Oumuamua was its acceleration. As it rounded the Sun and headed back toward interstellar space, it sped up beyond what purely gravitational calculations predicted. Not by much, just a tiny, almost imperceptible change in velocity. But it was there, statistically significant, and completely unexplained by standard orbital mechanics. When comets accelerate, it's because of the rocket effect from outgassing. Ice turns to vapor, jets away from the surface, and the conservation of momentum pushes the comet in the opposite direction. It's like a very slow, very inefficient rocket engine, but Oumuamua showed no coma, no tail, no spectroscopic evidence of any volatiles whatsoever. It appeared completely dry, more like an asteroid than a comet. Yet it was accelerating as if something was pushing it. Theories proliferated. Maybe it was a hydrogen iceberg, with frozen hydrogen sublimating without leaving visible traces, because hydrogen doesn't absorb or emit light efficiently in wavelengths we typically observe. Maybe it had a highly reflective surface, and radiation pressure from sunlight was pushing it more than normal. Maybe its shape, if truly as elongated as some measurements suggested, experienced unusual radiation forces. Maybe, as Harvard astronomer Avi Loeb famously proposed, it was artificial, a light sail built by an extraterrestrial civilization and sent on a journey through the galaxy. Most astronomers rejected the artificial hypothesis, but the fact remained. Oumuamua was weird, and we never got enough observations to truly understand it. It's long gone now, billions of kilometers away and receding at 26 kilometers per second toward the constellation Pegasus, carrying its secrets with it. We'll never catch up to it. We'll never get another look. It remains one of astronomy's most tantalizing mysteries, a visitor that arrived, confused us, and departed before we could gather the data needed to definitively explain its nature. 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov using a homemade 65cm telescope in Crimea, was refreshingly, almost disappointingly normal. Borisov built his telescope himself, grinding the mirror by hand, assembling the mount from parts, all in pursuit of his passion for discovering comets. On the night of August 30th, he captured images of a faint fuzzy object that didn't match anything in the catalogues. Follow-up observations revealed it was moving on a hyperbolic trajectory, travelling at 32 kilometers per second, unbound from the sun's gravity. Unlike Oumuamua, Borisov behaved exactly like a comet should. It had a clear, well-developed coma visible even in early observations when it was still far from the sun. It had a tail pushed back by solar radiation and the solar wind, always pointing away from the sun as cometary tails must. Spectroscopy revealed the unmistakable signatures of water vapour, carbon monoxide and cyanide, all sublimating from the nucleus as solar heating increased. Observations from observatories around the world, including the Hubble Space Telescope, the Very Large Telescope in Chile, and the ALMA Radio Observatory, built up a comprehensive picture of this object. Its nucleus was roughly half a kilometre across. Its composition was similar to comets formed in our own solar system's outer reaches, with water ice, carbon monoxide, and complex organic compounds mixed together. The ratios weren't identical to solar system comets. There was more carbon monoxide relative to water than we typically see, but they were close enough to suggest that comet formation processes might be universal. Borisov reached perihelion on December 8th, 2019, passing just 2 astronomical units from the Sun, about twice Earth's distance from our star. At that distance, it was well beyond the orbit of Mars, never getting particularly warm, but solar heating was sufficient to drive steady outgassing that produced a coma extending tens of thousands of kilometers from the nucleus. Professional and amateur astronomers monitored it for months, tracking how its brightness changed, measuring gas production rates, analysing dust properties. One particularly interesting observation came from Hubble, which watched as a chunk of the nucleus broke off sometime around mid-March 2020. The brightness increased suddenly, then faded back to normal levels, behaviour consistent with a fragmentation event where part of the comet's nucleus separated and created a brief surge in dust production before the fragments dispersed. This kind of fragmentation is common in solar system comets, especially those making close approaches to the Sun. The fact that Borisov did it too suggested that interstellar comets aren't necessarily more structurally robust than their solar system cousins. By mid-2020, Borisov had faded beyond the reach of most telescopes, heading back toward interstellar space on a trajectory that would eventually carry it into the outer Milky Way. Like Oumuamua, it's gone forever, but unlike Oumuamua, we understood it. It was a comet, formed in another star system, but fundamentally similar to the comets we see every year in our own solar system. It validated the idea that physics and chemistry work the same way throughout the galaxy, that the processes forming these icy bodies here also operate around other stars, and now we have 3i Atlas, active like Borisov, with clear cometary features including a coma, tail, and spectroscopic evidence of outgassing. But with anomalies that set it apart from both previous visitors. The anti-tail feature, prominent and persistent over months of observation, more pronounced than the typical perspective effects that sometimes create apparent sunward tails. The brightness variations fluctuating by half a magnitude or more over timescales of weeks, suggesting either an irregular nucleus with varying composition or internal structure that drives asymmetric outgassing patterns. Most significantly, the radio detection of hydroxyl, the first time anyone has ever picked up a radio signal from an interstellar object. The fact that this detection occurred at all, that MeerKAT managed to catch the comet during that narrow window when the geometry aligned and the chemistry was active, represents both technical achievement and fortuitous timing. The previous detection attempts in September came up empty, not because the technique was flawed, but because the comet simply wasn't producing enough hydroxyl yet. By late October, everything had changed, and the signal appeared exactly when and where theory predicted it should. What do these three objects tell us when we consider them together? First, that interstellar objects are diverse. They're not all the same. They can be dry and rocky like Oumuamua, or icy and active like Borisov and 3i Atlas. They can behave predictably, following our models of how comets should evolve, or they can surprise us with unexplained accelerations and unusual features. Second, that our solar system's comets and asteroids aren't unique. The chemistry that produces water ice, carbon dioxide, carbon monoxide, all mixed together in dirty snowballs, isn't special to our stellar neighbourhood. It happens throughout the galaxy, creating objects that look and behave remarkably like the comets we've studied for centuries in our own system. Third, that we still have a lot to learn. 3 confirmed interstellar objects isn't enough to draw definitive conclusions about population statistics, about what percentage are cometary versus asteroidal, about how their compositions vary with the type of star system they came from. We need dozens of detections, hundreds eventually, before we can start making confident statements about the broader population of these wanderers. And fourth, perhaps most importantly, that every interstellar visitor is an opportunity to measure chemistry from another star system, an opportunity to test our theories about how planetary systems form and evolve, an opportunity to glimpse, however briefly, the kind of material that exists throughout the galaxy, material that's been processed by radiation and collisions, that's travelled across light years of empty space, that now passes through our neighbourhood close enough to study before vanishing back into the dark. The contrast between Oumuamua's dry mystery, Borisov's wet normalcy, and 3i Atlas's active complexity tells us that the galaxy is full of surprises, that objects born around different stars, ejected by different mechanisms, carrying different compositions, all end up wandering the space between stellar systems. And occasionally, just occasionally, one of them passes close enough to our sun that we can point our telescopes at it and learn something fundamental about the universe beyond our own small corner of space. Before we dive deeper into what MeerKAT detected, it's worth stepping back to appreciate the broader context of radio astronomy and why this particular detection matters so much to the field. Radio astronomy is, in many ways, the unsung hero of modern astrophysics. While optical telescopes capture the imagination with stunning images of colourful nebulae and distant galaxies, radio telescopes quietly probe the universe in wavelengths invisible to human eyes, revealing phenomena that would otherwise remain completely hidden. Radio waves have wavelengths ranging from about 1 millimetre to over 100 metres, far longer than the wavelengths of visible light, which measure just hundreds of nanometers. This difference in wavelength gives radio astronomy several crucial advantages. Radio waves can penetrate dust clouds that completely block visible light, allowing astronomers to see into stellar nurseries where new stars are being born. Radio observations work day or night, unaffected by sunlight or weather conditions that can hamper optical astronomy. And perhaps most importantly for our story, radio waves can reveal the presence of specific molecules through their characteristic emission and absorption patterns. The history of radio astronomy is filled with unexpected discoveries. In 1933, Karl Jansky at Bell Telephone Laboratories was investigating static that interfered with radio communications when he discovered that some of the noise was coming from the Milky Way itself. This accidental finding opened an entirely new window on the universe. In 1967, Jocelyn Bell Burnell discovered pulsars, rapidly spinning neutron stars that beam radio waves like cosmic lighthouses. The discovery was so unexpected that the signals were initially nicknamed LGM-1 for little green men before their natural origin was confirmed. Radio telescopes have mapped the structure of our galaxy, traced the cosmic microwave background radiation left over from the Big Bang, discovered thousands of galaxies too distant or too obscured by dust to see optically, and revealed supermassive black holes at the centers of galaxies by detecting the radio emissions from matter spiraling into them. The Very Large Array in New Mexico has produced iconic images of radio sources across the sky. The Atacama Large Millimeter Array in Chile has captured stunning views of protoplanetary disks where planets are forming. The Event Horizon Telescope, a globe-spanning network of radio dishes working together, produced the first ever image of a black hole's shadow. But detecting molecules from an interstellar comet represents a different kind of challenge and achievement. Comets are small, faint, and their radio emissions are weak compared to the powerful sources that radio astronomy typically studies. The hydroxyl cloud around 3I Atlas, while large by cometary standards, is minuscule compared to the giant molecular clouds that span light years and emit radio waves so strongly they can be detected from across the galaxy. The sensitivity required to detect these faint signals is extraordinary. Radio telescopes must be able to distinguish a signal that's perhaps only a few times stronger than the background noise of the universe itself. They must filter out interference from Earth-based radio sources, everything from cell phones to microwave ovens to radio and television broadcasts. They must account for the motion of Earth, the rotation of the planet, the drift of the telescope platform, all of which can introduce systematic errors into the data. Modern radio telescopes achieve this sensitivity through several techniques. Large collecting areas, like MeerKAT's 64 dishes working together, gather more radio energy and improve the signal-to-noise ratio. Interferometry, the technique of combining signals from multiple dishes, provides both sensitivity and resolution that single dishes can't match. Sophisticated receivers cooled to temperatures just a few degrees above absolute zero reduce thermal noise that would otherwise swamp faint signals, and powerful computers process the incoming data in real time, correlating signals, filtering interference, and producing spectra with the resolution needed to detect individual molecular lines. The detection of hydroxyl from 3I Atlas required all of these techniques working perfectly together. The observation had to be planned carefully, timing it for when the comet was producing enough hydroxyl to be detectable, but before solar conjunction made observation impossible. The telescope had to track the comet's motion across the sky precisely, keeping it centered in the beam. The receivers had to be tuned to exactly the right frequencies, accounting for Doppler shift from the comet's velocity. The data processing had to remove interference and extract the faint absorption signal from the noisy background. Any one of these steps could have failed. The timing could have been slightly off, observing before the comet produced enough hydroxyl or after it had passed behind the Sun. The tracking could have been imprecise, causing the comet to drift out of the beam. The receivers could have malfunctioned. The data processing could have introduced artifacts that looked like signals but weren't real. The fact that everything worked, that all these pieces came together to produce a clear, unambiguous detection, is itself remarkable. This is why the September observations are so important to the story. Those failed attempts weren't failures in the sense that something went wrong. They were negative results that confirmed the technique was sound, but the timing wasn't right yet. The comet wasn't producing detectable amounts of hydroxyl in September because it was still too far from the Sun, still too cold. The fact that the October observation succeeded while the September observations didn't validates the entire approach and confirms that we're seeing real chemistry evolving as the comet warms. Let's talk about what MeerKAT actually detected on October 24th, because this is where the science gets truly beautiful. Hydroxyl radicals, those OH molecules showing up at 1.665 and 1.667 gigahertz, aren't some exotic compound found only in interstellar comets. They're everywhere in the universe. They're in interstellar clouds. They're in star-forming regions. They're around dying stars. They're in comet comas throughout our solar system. Hydroxyl forms when water molecules get hit by ultraviolet radiation from a star. Water, H2O, is a pretty stable molecule under normal conditions. But when you blast it with high-energy UV photons, it doesn't just evaporate peacefully. It breaks. the chemical bonds holding it together fracture violently. The hydrogen atoms, being light and fast, go flying off in one direction. The hydroxyl radicals, those OH molecules, linger behind like ghosts of their parent molecule. Here's the critical thing. Hydroxyl absorbs radio light at very specific frequencies, determined by the quantum mechanical properties of the molecule itself. When hydroxyl is present in a cloud of gas, and you point a radio telescope at it with a bright radio source behind it, the hydroxyl absorbs energy at exactly 1.665 and 1.667 GHz, creating dips in the spectrum. It's like a fingerprint, unique and unmistakable. Astronomers have been using hydroxyl absorption and emission to study comets for decades. It's one of the primary ways we measure water production rates, because you can't directly see water vapour in the optical spectrum very efficiently, but hydroxyl lights up like a beacon in the radio and ultraviolet bands. When you want to know how much water a comet is spewing into space, you measure the hydroxyl and work backward. So in one sense, finding hydroxyl around 3I Atlas is completely expected. It's a comet approaching the Sun. Of course it's producing hydroxyl. That's what comets do. But here's what makes this detection extraordinary. This is the first time anyone has ever detected a radio signal from an interstellar object. Ever. We've studied comets with radio telescopes countless times, but those were all solar system comets, objects born in our own stellar neighbourhood. 3I Atlas formed around a different star in a different planetary system carrying ice that assembled from the primordial material of that alien protoplanetary disk. What MeerKAT detected wasn't just hydroxyl. It was hydroxyl from another star system. It was direct chemical information about interstellar material, transmitted to us via the universal language of molecular spectroscopy. The MeerKAT observation on October 24th wasn't just lucky. It was the result of careful planning, exquisite timing, and a telescope that's among the best in the world for this kind of work. Let's break down exactly what happened and why it matters, because understanding the technical achievement helps us appreciate just how remarkable this detection really was. MeerKAT is a radio interferometer located in the Karoo Desert of South Africa, one of the most radio-quiet regions on Earth. It consists of 64 dishes, each 13.5 meters in diameter, spread across 8 kilometers of pristine desert. Each dish works in concert with the others, combining their signals in real time through a massive correlator, effectively creating a single virtual telescope far larger and more sensitive than any individual dish could be. The array specializes in what's called the L band, radio frequencies ranging from roughly 1 to 2 gigahertz. This is prime territory for detecting hydroxyl, and it's also relatively free from interference compared to other frequency ranges. The South African government has legally protected the Karoo from radio frequency pollution, meaning no cell towers, no Wi-Fi routers, no broadcast stations for hundreds of kilometers in any direction. This protection is crucial because even weak terrestrial signals can drown out the faint whispers from space that astronomers are trying to detect. When MeerKAT observed 3I Atlas on October 24th, the comet was located just 3.76 degrees from the Sun in the sky. Let me put that in perspective. Hold your fist at arm's length and extend your thumb. That's about 2 degrees of sky. 3I Atlas was less than twice that distance from the brightest object in the daytime sky, from Earth's perspective. The Sun floods the entire electromagnetic spectrum with radiation, drowning out everything around it in a blaze of radio noise. Most radio telescopes won't even attempt to observe that close to the solar disk, because the interference is overwhelming. It's like trying to hear a whisper at a rock concert while standing next to the speakers. But geometry is everything in astronomy. The fact that 3I Atlas was so close to the Sun didn't just make the observation difficult. In a strange way, it actually helped. Here's why. When an object moves through space, its velocity causes a Doppler shift in any radiation it emits or absorbs. If it's moving toward you, wavelengths compress and shift toward the blue end of the spectrum. If it's moving away, they stretch and shift toward the red. This is the same effect that makes an ambulance siren sound higher pitched, as it approaches, and lower pitched as it drives away, but for light and radio waves instead of sound. 3I Atlas was travelling through the inner solar system at an angle, not directly toward or away from Earth. The measurements showed a recession velocity of approximately minus 15.6 kilometers per second for both hydroxyl lines, based on the Doppler shift observed. This shift nudged those absorption features just far enough from the sun's overwhelming radio output that MeerKAT's receivers could pick them out of the noise. If the comet had been moving at a different velocity, or if the observation had been attempted from a different angle, the hydroxyl lines might have been completely swamped by solar interference. The line widths were equally telling. Measurements showed values of approximately 0.88 and 1.26 kilometers per second, measured as full width at half maximum. These are narrow, precise, repeatable across multiple scans. If this had been instrumental noise or radio interference, the lines would have been broader, messier, inconsistent from one observation to the next. But they held steady, like a tuning fork ringing at a single clear frequency, exactly as you'd expect from real hydroxyl molecules in a comet's coma. The data integrity checks passed every test. The signal was real, and it was coming from exactly where 3I Atlas should have been based on its predicted ephemeris, the calculated path through space that astronomers use to know where to point their telescopes at any given moment. The position matched within the uncertainties, the velocity matched, the line strengths matched what models predicted for a comet at that distance and temperature. Perhaps most importantly, this wasn't the first time astronomers had tried to catch 3I Atlas in the radio spectrum. MeerKAT had attempted observations on September 20th and September 28th. Both attempts came up empty. Total silence. No hydroxyl, no emission lines, no absorption features, nothing. The telescope was working perfectly, the observations were executed correctly, the comet just wasn't producing detectable amounts of hydroxyl yet. So why did it appear on October 24th? The answer comes down to temperature and timing, and it reveals something fundamental about how comets work. In late September, the comet was still too far from the sun, still too cold for significant sublimation of water ice. The surface temperature was below the threshold where volatiles really start to cook off in large quantities. Water ice needs to reach around 190 to 200 Kelvin before sublimation becomes vigorous enough to produce detectable amounts of gas. But by late October, everything changed. The comet was days away from perihelion, and the sun's radiation was hammering its surface with increasing intensity. Ice that had remained frozen for millions or billions of years was finally warming up, cracking, releasing gas into the thin atmosphere surrounding the nucleus. And with that gas came hydroxyl radicals, billions upon billions of them per second, forming a cloud that absorbed radiolight at exactly the frequencies MeerKAT was designed to detect. At the time of the detection, 3I Atlas was 1.38 times farther from the Sun than Earth, placing it at about 1.38 astronomical units, or roughly 206 million kilometers from our star. At that distance, the solar flux, the amount of energy hitting each square meter of the comet's surface per second, is significantly less than what Earth receives. Solar heating decreases with the square of the distance, so at 1.38 AU, the comet was receiving about 52% of the solar energy that hits Earth. But that was enough. Based on standard models of how cometary surfaces absorb and radiate energy, astronomers estimated the surface temperature of 3I Atlas at around 230 Kelvin, or about minus 43 degrees Celsius. That's cold by terrestrial standards, but it's warm enough for water ice to sublimate directly from solid to gas without melting first. At that temperature, the ice begins to crack and release vapor into the surrounding space, forming what astronomers call a coma, a thin atmosphere of gas and dust that envelops the nucleus. The thermal motion of hydroxyl molecules at 230 Kelvin generates a natural line broadening that you can calculate from basic physics. The relationship between temperature and line width is well understood, and the predicted broadening at this temperature is about 0.8 kilometers per second, measured as full width at half maximum. That matches almost perfectly with what MeerKAT observed, providing independent confirmation that the detection is real and that the temperature estimate is reasonable. The timing window for this detection was almost cruelly narrow. Too early, and the volatiles haven't released yet as the September observations proved. Too late, and the object swings behind the Sun from Earth's perspective, becoming completely unobservable as it reaches perihelion. The solar conjunction, when the comet passed directly behind the Sun from our point of view, occurred just days after the detection. October 24th fell right in the sweet spot, a brief interval when the geometry aligned, the chemistry activated, and the sensitivity of the instrument matched the strength of the signal. If MeerKAT had observed even 48 hours later, the detection might have been impossible. the solar conjunction would have swallowed the object entirely, hiding it behind a wall of radio interference that no telescope on Earth could penetrate. The astronomers who planned this observation knew they had one chance, one narrow window to catch the comet in the radio spectrum before it disappeared behind the Sun. They took that chance, and it paid off with the first radio detection of an interstellar object in human history. Now we need to address the elephant in the room, the coincidence that's generated more headlines and speculation than perhaps any other aspect of this story. When 3I Atlas was detected on October 24th, it was located at approximately 19 hours right ascension and minus 27 degrees declination in the sky. That's remarkably close to one of the most famous coordinates in the history of the search for extraterrestrial intelligence. On August 15th, 1977, the Big Ear Radio Telescope in Ohio picked up a strong narrowband radio signal at 1420.4 MHz, right next to the hydrogen line. The signal was so powerful that astronomer Jerry Eman, reviewing the computer printout days later, circled the alphanumeric sequence representing its intensity and wrote "wow" in the margin. The wow signal originated from near 19 hours 25 minutes right ascension and minus 26 degrees 45 minutes declination. That's in the constellation Sagittarius, toward the galactic center. The signal lasted for 72 seconds, exactly as long as the Big Ear's observing window allowed. It was narrowband, intense, and bore all the hallmarks of something artificial, and it never repeated. Despite hundreds of hours of follow-up observations over subsequent decades, no one has ever detected it again. Theories about the wow signal have ranged from alien transmissions to passing comets, releasing hydrogen clouds to interstellar scintillation effects amplifying natural emissions. In 2017, astronomer Antonio Paris suggested that comets 266P, Christensen, and 335 Pipame-Gibbs might have been responsible, as they were in the vicinity at the time and could have produced hydrogen emissions. But others pointed out problems with that hypothesis. Comets don't typically produce radio signals strong enough to explain what Big Ear detected, and the signal's narrowband characteristics didn't quite match what you'd expect from cometary outgassing. More recently, in 2025, researchers analysing archival data from the Arecibo Radio Telescope suggested the signal might have been caused by stimulated emission of hydrogen, due to a transient radiation source like a magnetar flare, a sudden burst of energy from a highly magnetized neutron star. That explanation has gained some traction, but like all the others, it remains unproven. And now, 48 years after the wow signal, another anomalous detection has occurred in nearly the same region of the sky, separated by approximately 9 degrees of arc. That's roughly 18 times the width of the full moon, on the celestial sphere, which spans 360 degrees in all directions. That's close enough to catch attention. Close enough that when the hydroxyl detection from 3I Atlas was announced, SETI researchers immediately started pulling up archival data, comparing notes, wondering if there could possibly be any connection at all. Avi Loeb, the Harvard astronomer who had encouraged radio, observatories like MeerKAT to monitor 3I Atlas specifically because of its proximity to the wow signal region, called the detection the first radio signal from 3I Atlas, carefully framing it as an interstellar chemistry milestone while acknowledging the tantalizing coincidence. But let's be absolutely clear about something. The hydroxyl detection from 3I Atlas is not the wow signal. It's not even the same type of signal. The wow signal was a narrowband emission at 1420 MHz, appearing as a spike in intensity. The 3I Atlas detection is an absorption line at 1665 and 1667 MHz, appearing as dips in the spectrum where hydroxyl molecules removed energy from background sources. One was potentially artificial, displaying characteristics that made it stand out as anomalous. The other is completely natural, perfectly consistent with known cometary chemistry. One lasted 72 seconds and never repeated. The other appeared in a comet we've been tracking for months, exactly when and where we expected hydroxyl to show up, based on the comet's distance from the Sun and its thermal state. The connection between 3I Atlas and the wow signal region is almost certainly pure coincidence. Sagittarius is toward the galactic center, one of the richest and most observed regions of the sky. More telescopes point in that direction more often than almost anywhere else, which means more data, more observations, more chances to catch something unusual. The fact that two anomalous detections happened in roughly the same area 48 years apart probably doesn't mean anything more than that astronomers spend a lot of time looking at that part of the sky. But the coincidence is striking enough to note. 9 degrees might sound like a lot, but in terms of galactic structure, it's practically next door. If you were trying to send a probe into a star system, and you wanted to approach from a direction that wouldn't raise immediate red flags, coming from a region already associated with mysterious radio signals might be a clever strategy. Not that there's any evidence for that. Not that we should jump to that conclusion. But the human mind loves patterns, loves coincidences, loves to see meaning where there might only be randomness. And sometimes, just sometimes, coincidences aren't random at all. Let's focus on what we actually know, on what the detection tells us about 3I Atlas and the planetary system where it formed. The hydroxyl radicals MeerKAT detected are the products of water photodissociation, water molecules breaking apart under solar ultraviolet radiation. That means 3I Atlas contains water ice. A lot of it, actually, based on the strength of the absorption lines and the estimated size of the hydroxyl cloud surrounding the nucleus. But here's the thing. This isn't the first time water has been detected from 3I Atlas. In early October, NASA's Neil Gehrels Swift Observatory observed the comet using its ultraviolet telescope and detected hydroxyl gas, the same OH molecules that MeerKAT would later confirm in the radio spectrum. Swift saw the faint UV glow that hydroxyl produces when it absorbs solar ultraviolet light and re-emits it at different wavelengths. The researchers analysing that data found clear evidence of water sublimation occurring, though quantifying exact production rates for such a faint, distant object comes with considerable uncertainty. The James Webb Space Telescope also turned its powerful infrared instruments toward 3I Atlas in early August, using its near-infrared spectrograph to analyse the comet's composition. Initial results suggested the comet might be rich in carbon dioxide ice, with water accounting for a smaller fraction of its total volatile budget based on early measurements, though different observation epochs and techniques can yield varying results as the comet's activity evolves. That would make it somewhat different from typical solar system comets, which are generally much richer in water. But here's where it gets interesting. Different instruments measuring at different wavelengths and different times in the comet's evolution can produce seemingly contradictory results. Carbon dioxide sublimates at much lower temperatures than water, around 150 Kelvin compared to 200 Kelvin for water. So if JWST observed 3I Atlas when it was still relatively far from the Sun and cold, it might have been catching the initial stages of carbon dioxide outgassing, before the water really started flowing. By the time Swift and then MeerKAT observed the comet in October, it was much closer to the Sun, much warmer, and the water production had ramped up dramatically. The hydroxyl detection doesn't contradict the earlier carbon dioxide observations. It just shows that the comet's chemistry is evolving as it approaches perihelion, with different volatiles dominating at different distances and temperatures. What the combined observations tell us is that 3I Atlas contains both carbon dioxide and water, along with all the other usual cometary suspects: carbon monoxide, methane, ammonia, and complex organic compounds. The ratios might be slightly different from typical solar system comets, reflecting different formation conditions in that distant planetary system, but the basic chemistry is the same, and that's profound. That's evidence that the building blocks of life, the molecules that make biology possible, aren't unique to our solar system. Water formed around another star billions of years ago still behaves the same way our water behaves. The laws of chemistry are universal. The same molecules that fill Earth's oceans exist out there, frozen into comets and asteroids, drifting through the galaxy. Dennis Bodowitz, a professor of physics at Auburn University and part of the team analysing the Swift observations, put it beautifully. When we detect water, or even its faint ultraviolet echo, IHATS, from an interstellar comet, we're reading a note from another planetary system. It tells us that the ingredients for life's chemistry are not unique to our own. That note, written in hydroxyl radicals and transmitted across interstellar space via radio waves, says something fundamental about the universe. Life's ingredients are everywhere. They're common, they're mobile, and they travel between stars on cosmic lifeboats like 3I Atlas, carrying the chemistry of one planetary system to another. October 29th, 2025, perihelion, the moment 3I Atlas reached its closest point to the Sun approximately 203 million kilometres away, just inside the orbit of Mars. At that distance, the Sun's gravitational pull was immense, whipping the comet around in a tight curve and flinging it back toward interstellar space at even higher velocity than it arrived. But here's the problem: we couldn't see it. Earth was on the opposite side of the Sun. From our perspective, 3I Atlas had vanished behind the solar disk, hidden in the glare of our star. Ground-based telescopes were useless. Even space telescopes like Hubble and JWST orbiting Earth couldn't observe through the Sun's overwhelming brightness. For several weeks, 3I Atlas was invisible to humanity. The most interesting phase of its journey, when solar heating should have been at maximum and volatile release should have peaked, occurred when no Earth-based instrument could watch. It was maddening for astronomers who had been tracking this visitor for months, documenting every aspect of its behaviour, building models of its composition and structure. But we weren't completely blind. On October 3rd, 3 Atlas passed within roughly 30 million kilometres of Mars, close enough that spacecraft orbiting the red planet could observe it. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter turned their instruments toward the comet, capturing images and spectra from a vantage point that Earth-based telescopes couldn't match. These observations, still being analysed as of November, might provide crucial data about what the comet was doing during its closest approach to the Sun. NASA's Juno spacecraft, currently studying Jupiter and its moons, is also planning observations of 3I Atlas in March 2026, when the comet passes within 53 million kilometres of the giant planet. Juno will use its dipole antenna to search for low-frequency radio emissions ranging from 50 Hz to 40 MHz, frequencies that ground-based telescopes can't easily observe due to Earth's ionosphere blocking those wavelengths. But for now, in mid-November 2025, 3I Atlas has re-emerged from behind the Sun, climbing back into the morning sky as seen from Earth. Ground-based telescopes are picking it up again, documenting its post-perihelion state, checking to see if it survived the intense solar heating intact, or if it fragmented like some comets do when thermal stress overwhelms their structural integrity. Early reports are encouraging. Images from the Nordic Optical Telescope on November 11th show a single body with no evidence of breakup. The Virtual Telescope project captured images on November 10th and 11th showing that the comet's ion tail has grown dramatically longer and more structured, a sign of intensifying activity even as it begins its journey back toward the outer solar system. The most striking feature in these post-perihelion images is what observers are calling a sunward jet, an elongation in the coma pointing directly toward the Sun. This antitail is similar to features Hubble observed back in July, suggesting that whatever process is creating it has been consistent throughout the comet's passage. The leading theory is that this is caused by dust grains released earlier in the orbit, now lagging behind the nucleus and creating the illusion of a tail pointing in the wrong direction, due to viewing geometry. But the symmetry is unusual. Most antitails are faint compared to the main tail, visible only under certain very specific viewing angles. The antitail on 3I Atlas has been prominent from multiple observing geometries, suggesting something more complex than simple perspective effects. Perhaps the nucleus is spinning rapidly with active regions at opposite poles, firing jets aligned with the rotation axis. Perhaps there's an internal structure with volatiles concentrated in specific locations that create asymmetric outgassing patterns. We won't know for sure without better observations, ideally from spacecraft close enough to resolve the nucleus directly. But for now, the post-perihelion images confirm one crucial fact. 3I Atlas survived. It didn't fragment, it's still active, and it will continue to be observable for months as it climbs higher in the morning sky, eventually reaching its closest point to Earth on December the 19th at a distance of 270 million kilometres. That's still incredibly far, more than twice the distance to Mars at opposition, but it will be the best opportunity for Earth-based telescopes to study this interstellar visitor before it fades back into the darkness forever. One of the most puzzling aspects of 3I Atlas has been its brightness behaviour. When it was first discovered in July, it was shining at around 17th to 18th magnitude, extremely faint, visible only to large telescopes. By September, it had brightened to between 12th and 14th magnitude, still too faint for amateur observers, but within reach of moderate-sized instruments. Then, as it approached perihelion in late October, something unexpected happened. The comet suddenly brightened much faster than models predicted, becoming visible to space observatories at magnitude 7 to 8. This dramatic outburst, likely caused by water, ice becoming active as sunlight penetrated deeper layers beneath the surface, proved that 3I Atlas was far more dynamic than early observations suggested. Now, in November, the comet is shining at around magnitude 11 to 12 under normal conditions, though some forecasts suggest it could briefly reach magnitude 9 if its heightened activity continues. That would make 3I Atlas the brightest interstellar object ever observed, surpassing even 2I Borisov at its peak. But brightness in astronomy is a complicated thing. A comet's magnitude depends not just on its size and distance, but on how much dust and gas it's releasing, how reflective that material is, and the viewing geometry between the comet, the Sun, and Earth. A sudden outburst can increase brightness by factors of 10 or more in just days, while a return to quiescence can dim it just as quickly. The brightness variations 3 Atlas has shown, fluctuating by nearly half a magnitude over the course of weeks, are more extreme than simple rotational modulation should produce. A half magnitude change corresponds to about a 60% increase in brightness, which would require either a sudden increase in dust production or a change in viewing geometry that exposed a more reflective surface. But the orbit is well known, the viewing geometry is predictable, and no sudden massive outbursts have been observed in real time. The brightness just changes, smoothly but significantly, as if the comet is responding to factors that aren't immediately obvious from the data. One possibility is that the nucleus has an irregular shape with different regions having different compositions and thermal properties. As it rotates, bringing different facets into sunlight, the amount and type of outgassing changes, affecting the brightness. Another possibility is that subsurface heating is driving the activity, with sunlight penetrating the outer layers of ice and heating the interior, causing pressure to build until gas erupts through cracks and vents in unpredictable patterns. Or maybe, just maybe, there's something about the internal structure of this interstellar visitor that we don't understand yet. Something about how ice accumulated and froze in that distant protoplanetary disk billions of years ago, creating a comet that behaves just differently enough from solar system comets to keep astronomers guessing. How old is 3I Atlas? It's a simple question with a complicated answer. Research teams analysing the comet's trajectory and origins have proposed something remarkable. Based on where it appears to have come from in the galaxy and models of how interstellar objects get ejected from their home systems, some estimates suggest 3I Atlas could be extraordinarily ancient, potentially at least 7 billion years old. This would make it roughly twice as old as Earth, potentially the oldest comet humanity has ever observed. However, these estimates carry significant uncertainties, as pinning down the exact age of an interstellar object requires making assumptions about when it was ejected and what path it took through the galaxy. Based on these estimates, if 3I Atlas truly is that ancient, it could have formed when the universe itself was less than half its current age. The Milky Way had a very different structure then. The Sun and Earth didn't exist yet. The star system where 3I Atlas formed might not exist anymore. Main sequence stars with masses significantly larger than our Sun live fast and die young, burning through their nuclear fuel in a few billion years before exploding as supernovae. If the age estimates are even close to accurate, 3I Atlas has been wandering through the galaxy for an almost incomprehensible span of time. It's been bombarded by cosmic rays, high-energy particles from supernova remnants, and active galactic nuclei that can alter the chemistry of surface ices. Observations from the James Webb Space Telescope have found evidence suggesting cosmic radiation has indeed altered the comet's outer layers, consistent with a long journey through interstellar space. The comet might have passed through giant molecular clouds, those stellar nurseries where new stars are being born, potentially accumulating thin coatings of dust and organic molecules along the way, and now, by sheer chance, its path has intersected with ours. The gravitational influence of our Sun reached out across the light years and gently, almost imperceptibly, altered 3I Atlas's trajectory, bending its path inward toward our planetary system. The comet didn't choose to come here. It didn't aim for us. The universe just worked out this way, and for a few months in late 2025, this ancient visitor from another star system passes through our neighbourhood, close enough to study before vanishing back into the dark. The ice on its surface, the organics mixed into that ice, the very atoms and molecules that make up its nucleus, all formed in conditions that might have been radically different from those in our own solar system. Different ratios of elements in the protoplanetary disk, different temperatures at different distances from the parent star, different radiation environments, different planetary giants orbiting at different distances, stirring the disk in different ways. Every measurement we make of 3i Atlas, every spectrum we capture, every image we analyze tells us something about planetary system formation beyond our own solar system. It's a sample, delivered to our doorstep, of the kind of material that exists out there. And based on what we've seen so far, it's not that different from our own comets. The chemistry is familiar. The physics is recognizable. The universe, it seems, follows the same rules everywhere. To truly appreciate what we're seeing with 3i Atlas, it helps to understand what comets actually are and how they work. The popular image of comets as dirty snowballs isn't wrong, but it's oversimplified. Modern observations have revealed that comets are complex objects with internal structure, varying compositions and behaviors that can surprise even experienced astronomers. A comet nucleus is typically a few hundred meters to a few tens of kilometers across, a small body by solar system standards. But packed into that small volume is a mixture of materials that tells the story of the early solar system, or in the case of interstellar comets, the story of another star system entirely. Water ice makes up a significant fraction of most comets, perhaps 50 to 80% by mass. But mixed with that water ice are other volatile compounds: carbon dioxide, carbon monoxide, methane, ammonia, and more complex organic molecules including amino acids and nucleobases, the chemical building blocks of proteins and DNA. These volatiles are frozen solid in the cold depths of space, temperatures hovering just a few tens of degrees above absolute zero. At those temperatures, even carbon dioxide, which sublimates at 194 Kelvin at Earth's atmospheric pressure, remains frozen solid. The ice is mixed with dust, tiny grains of silicate minerals and carbonaceous material that gives comets their characteristic dark surfaces. When you look at images of comet nuclei taken by spacecraft that have visited them, they don't look white and pristine like fresh snow. They look dark, almost black, coated with a layer of dust and organics that insulate the ice beneath. As a comet approaches the Sun, solar radiation begins to warm the surface. At first, nothing much happens. The outer layers, that dark crust of dust and refractory organics, absorb sunlight and warm up, but the insulating effect prevents heat from penetrating deep into the interior. But as the comet gets closer and the solar heating intensifies, the temperature reaches critical thresholds where different volatile compounds begin to sublimate. Carbon dioxide is often the first to go, starting to sublimate vigorously at around 150 Kelvin. This early outgassing can begin when the comet is still beyond Jupiter's orbit, far from the Sun. Water ice starts sublimating significantly at around 190 to 200 Kelvin, typically when the comet is somewhere between Mars and Earth's orbit. More volatile species like carbon monoxide can sublimate at even lower temperatures, though they may have been lost during previous passages close to a star or during the object's long journey through interstellar space. The sublimation process isn't uniform across the nucleus. Some regions may be richer in volatiles, while others have lost their ices through previous heating cycles and are now just inert rock and dust. Active areas can be concentrated at specific locations, perhaps where cracks or fissures in the crust allow gas to escape, or where the rotation of the nucleus brings fresh ice into direct sunlight. These active regions create jets, collimated streams of gas and dust that shoot away from the nucleus at speeds of hundreds of meters per second. The gas and dust released by sublimation form the coma, that diffuse cloud surrounding the nucleus that gives comets their fuzzy appearance. The coma can extend tens of thousands or even hundreds of thousands of kilometers from the nucleus, far larger than the nucleus itself. Gas molecules in the coma are then affected by solar radiation. Ultraviolet light from the sun breaks apart water molecules through photodissociation, creating the hydroxyl radicals that MeerKAT detected. It also ionizes other molecules, stripping away electrons and creating a plasma that interacts with the solar wind. This interaction with the solar wind creates the ion tail, that long straight tail that always points directly away from the sun. The ions are charged particles, and they're swept away by the solar wind's magnetic field, streaming behind the comet in a tail that can stretch for millions of kilometers. Separately, the dust released by the nucleus forms the dust tail, broader and curved, following the comet's orbital path. Larger dust grains respond more slowly to radiation pressure, so they lag behind, creating that characteristic curved appearance. All of this activity, the sublimation and photodissociation and plasma interactions, creates the spectacular display that makes bright comets visible from Earth. But it also creates challenges for astronomers trying to understand what's happening. The coma obscures the nucleus, making it difficult to see the solid body at the comet's heart. The jets and outbursts can be unpredictable, driven by internal structure we can't observe directly. The dust scatters and absorbs light, affecting brightness measurements. The gas creates a complex three-dimensional environment where molecules at different distances from the nucleus experience different radiation fields and temperatures. For 3I Atlas, all of these processes are playing out just as they would for a solar system comet. The hydroxyl detection tells us that water ice is sublimating and being broken down by solar UV radiation. The visible coma tells us that dust is being released along with the gas. The tail formation tells us that radiation pressure and solar wind are affecting the material just as they should. In all these respects, 3I Atlas is behaving like a perfectly normal comet. But there are those nagging anomalies. The anti-tail that's more prominent than perspective effects alone can easily explain. The brightness variations that seem excessive for simple rotation. The fact that activity appears to have increased, or at least maintained its level after perihelion, when many comets quiet down. These details suggest that maybe, just maybe, there's something about the internal structure or composition of this interstellar visitor that's different from what we typically see. One possibility is that 3I Atlas has a highly porous structure, more like a loosely bound pile of rubble than a solid chunk of ice. If the nucleus is full of voids and fractures, sunlight could penetrate deeper into the interior, warming ice that would normally be insulated by outer layers. This could drive outgassing from unexpected locations and maintain activity even as the comet recedes from the Sun. Another possibility is compositional layering. If 3I Atlas formed in a protoplanetary disk with different temperature gradients than our own, it might have layers with different volatile abundances. Maybe the outer layers were depleted in certain compounds during its interstellar journey, while deeper layers remain rich in ices. As solar heating penetrates deeper, it would expose these richer layers, driving the continued or increased activity we're seeing post-perihelion. Or perhaps the rotation state is more complex than simple spinning. Some comets tumble chaotically, rather than rotating smoothly around a single axis. This tumbling can bring different parts of the surface into sunlight in patterns that are difficult to predict, creating irregular brightness variations and unexpected jet directions. Without high-resolution images of the nucleus itself, we can only infer the rotation from the patterns we see in the coma and tail. What we're learning is that, even when something looks like just a comet, the details matter. The small differences in structure and composition between comets can tell us about the conditions where they formed, the processing they've undergone, the history written into their ice and dust. For solar system comets, we can sometimes trace this history back to specific regions of the protoplanetary disk where they originated. For interstellar comets, we're trying to read an even older history, one that might extend back billions of years to a star system that could be anywhere in the galaxy. One of the fundamental challenges with interstellar objects is that we get only one chance to study them. Solar system comets can return on predictable schedules. Halley's Comet comes back every 76 years, regular as clockwork. Even long-period comets, those with orbital periods measured in thousands or millions of years, are at least gravitationally bound to the Sun. If we miss an opportunity to observe them on one pass, we can plan for the next one, even if that next opportunity is generations or millennia away. But interstellar visitors are different. They're passing through on hyperbolic trajectories, moving too fast to be captured by the Sun's gravity. Once they leave, they're gone forever. We get months, maybe a year or two if we're lucky, to make all the observations we'll ever make. There are no second chances. If we miss a crucial measurement because the weather was bad or the telescope was scheduled for another project, or the comet was in solar conjunction, that data is lost forever. This creates enormous pressure to observe these objects as thoroughly as possible during their brief visits. Every clear night is precious. Every hour of telescope time is valuable. astronomers coordinate campaigns involving observatories around the world, handing off observations as Earth rotates so that the comet is under continuous surveillance. Data is analysed quickly, sometimes within hours of being collected, so that plans can be adjusted based on what's being seen. The economics of telescope time add another layer of complexity. Major facilities like the Hubble Space Telescope or the James Webb Space Telescope have schedules planned months or even years in advance. When an interstellar object is discovered, it can be difficult to get observing time unless the object is deemed sufficiently important to warrant interrupting planned programs. This is why rapid follow-up observations often come from smaller, more flexible facilities that can respond quickly to targets of opportunity. For 3I Atlas, the discovery in early July gave astronomers a relatively long lead time before perihelion in late October. That 4-month window allowed for planned campaigns rather than panicked scrambles. Observatories could submit proposals, justify the scientific importance, secure telescope time. JWST observed in August. Swift watched throughout September and October. MeerKAT planned its radio observations carefully, attempting them in September and then succeeding in October when conditions were right. But imagine if the discovery had come later, if 3 Atlas hadn't been spotted until September, when it was already approaching perihelion. The window for observation would have been measured in weeks rather than months. Some observations simply wouldn't have been possible. The careful planning that enabled MeerKAT's success might not have had time to happen. We might have missed the hydroxyl detection entirely. This is why improving our ability to discover these objects earlier is so important. The Vera C. Rubin Observatory, when it begins full operations, will scan the sky so thoroughly that it should catch interstellar visitors months before they reach the inner solar system, possibly even while they're still beyond Jupiter's orbit. That advance warning will transform how we study these objects, giving time to plan comprehensive campaigns, to coordinate multiple facilities, to maximize the scientific return from each precious visitor. Early detection also raises the possibility of spacecraft missions. Sending a probe to an interstellar object isn't easy. These visitors move fast, tens of kilometers per second, which means any spacecraft trying to intercept them needs a huge amount of delta V, the change in velocity required to match orbits. That requires either enormous amounts of fuel or gravity assist from planets, both of which take time to arrange. The Comet Interceptor mission is designed to sidestep some of these challenges by waiting in space rather than launching from Earth when a target is discovered. Parked at the Lagrange L2 point, it's already in a location where relatively modest velocity changes can send it on intercept courses, with comets approaching from many different directions. If an interstellar object is discovered early enough, Comet Interceptor could potentially be redirected to fly past it, capturing close-up images and measurements that ground-based and space-based telescopes simply can't provide. But even Comet Interceptor has limits. It can't catch objects that are already too close when discovered, or those approaching from unfavourable angles, or those moving so fast that the intercept requires more delta V than the spacecraft has available. For truly comprehensive spacecraft exploration of interstellar objects, we'd need a fleet of probes, each waiting in different orbital configurations, ready to respond to targets appearing from any direction. That's an expensive proposition, and it's not clear when or if space agencies will commit to such a program. In the meantime, we make do with what we have. Ground-based telescopes capturing images and spectra, space telescopes providing views unaffected by Earth's atmosphere, radio telescopes detecting molecules, all coordinated to squeeze every bit of information from these fleeting visitors before they vanish back into the dark. It's a race against time, against orbital mechanics, against the geometry that dictates when and where we can observe, and every success, like MeerKAT's hydroxyl detection, is a victory won against those constraints. The detection of water, or more precisely its breakdown product hydroxyl, from 3I Atlas, connects to one of the most fundamental questions in planetary science. Where does Earth's water come from? This might seem like a simple question with an obvious answer. Earth is covered in water, it's always been here, but the reality is far more complicated and interesting. When Earth formed 4.5 billion years ago, it coalesced from the protoplanetary disk surrounding the young sun. The inner solar system, where Earth orbits, was hot, very hot. Temperatures close to the sun were high enough to vaporize even refractory materials like rocks and metals. Water ice, which needs temperatures below roughly 170 Kelvin to remain stable, couldn't exist close to the Sun. The snow line, the distance from the Sun where water ice could condense, was located somewhere beyond the asteroid belt, past where Mars orbits today. This creates a problem. If Earth formed inside the snow line where water couldn't condense, how did our planet end up with oceans covering 70% of its surface? The answer, most planetary scientists believe, is that water was delivered to Earth after its initial formation, brought by comets and asteroids from the outer solar system where ice could survive. But how much water came from comets versus asteroids? And critically for our story, could some of Earth's water have come from interstellar sources? The ratios of different hydrogen isotopes in water can help answer these questions. Normal hydrogen has one proton. Deuterium, heavy hydrogen, has one proton and one neutron. The ratio of deuterium to hydrogen varies depending on where and how the water formed. Water in Earth's oceans has a specific deuterium to hydrogen ratio, about 156 parts per million. Water in comets from the Oort cloud, that distant reservoir of icy bodies at the outer edge of the solar system, tends to have higher deuterium ratios, around 300 parts per million. Water in Jupiter family comets, those with shorter orbital periods that likely originated in the Kuiper belt beyond Neptune, has ratios closer to Earth's oceans. Asteroids, particularly those from the outer main belt, also have deuterium ratios similar to Earth's water. These measurements suggest that most of Earth's water probably came from asteroids and Kuiper belt comets rather than Oort cloud comets. But the story is still incomplete. Measurements vary from comet to comet. Some show Earth-like ratios, others are enriched in deuterium. The sample size is still small, and we're learning that the distribution of water and its isotopic composition in the early solar system was more complex than simple models predicted. Now add interstellar comets to this picture. If 3I Atlas and objects like it contain water, and if such objects occasionally collided with Earth during its formation, they could have contributed to our planet's inventory. We don't know the deuterium ratio in 3I Atlas's water yet. That measurement would require either spacecraft analysis or extremely high-resolution spectroscopy that's beyond current capabilities for such a faint, distant object. But future measurements of interstellar comets could reveal whether their isotopic signatures match Earth's oceans, providing another clue to our planet's water budget. The broader point is that water isn't special to our solar system. The MeerKAT detection confirms what we've suspected but couldn't directly prove. Interstellar comets carry water just like solar system comets. They form in protoplanetary disks where temperatures are low enough for ice to condense. They survive ejection into interstellar space and the long journey through the galaxy, and when they encounter another star, that ice sublimes and produces the same chemical signatures we see in comets that never left our solar system. This universality is profound. It means the processes that led to Earth having water, having oceans, having the liquid medium necessary for life to emerge, aren't unique to our history. They're happening or have happened around countless other stars. Wherever rocky planets form in the habitable zone, that region where temperatures allow liquid water on the surface, there's likely a delivery system ready to bring water from the colder outer reaches of the system. Of course, having water doesn't guarantee life. Mars had water, probably oceans worth, but it lost most of it as its atmosphere was stripped away by the solar wind after its magnetic field died. Venus might have had water too, but a runaway greenhouse effect boiled it all away. Earth kept its water through a combination of factors: the right distance from the Sun, a protective magnetic field, plate tectonics that recycled carbon and regulated the climate, a large moon that stabilized its rotation axis. The list goes on, but water is the first requirement. Without it, life as we know it simply cannot exist. And what 3I Atlas tells us, what every interstellar comet we detect will tell us, is that water is out there. It's common, it's mobile, and it's being redistributed through the galaxy constantly, on icy bodies that travel between stars, delivering the essential ingredient for life to any world they happen to encounter. Let's talk about that sunward jet, that anti-tail that's been showing up in images since July. When a comet approaches the Sun, solar radiation pressure and the solar wind push dust and gas away from the nucleus, creating a tail that always points away from the Sun. Always. It's one of the most reliable features of cometary behaviour, so fundamental that ancient civilizations noticed it thousands of years ago. But 3E Atlas has developed what observers describe as an anti-tail, a secondary dust stream pointing in the opposite direction toward the Sun. Anti-tails aren't unheard of. They can appear as perspective effects when Earth passes through the orbital plane of a comet, creating the illusion of a tail pointing sunward when you're really seeing dust grains that were released earlier and are now lagging behind the nucleus. The phenomenon works like this. Imagine a comet travelling along its orbit, continuously releasing dust particles. These particles don't instantly fly away from the comet. Instead, they slowly drift away, responding to radiation pressure and their own orbital dynamics. Larger particles, those with more mass, respond more slowly to radiation pressure and tend to stay closer to the comet's orbital path. When Earth passes through or near the plane of this dust trail, we see it edge on, and it can appear to extend in front of the comet, creating the illusion of a tail pointing toward the Sun. But the symmetry in 3I Atlas's case is striking and has caught the attention of researchers worldwide. The main tail and the anti-tail have appeared with similar brightness and similar length in multiple observations separated by months, as if the comet is spewing material in two opposite directions simultaneously with comparable force. That's unusual. Most anti-tails are faint compared to the main tail, visible only under very specific viewing angles, and only in long exposure images taken under excellent conditions. For 3I Atlas, the anti-tail has been prominent from multiple observing geometries over several months. The Hubble space. Telescope imaged it in late July when the comet was still approaching perihelion. The feature appeared in ground-based observations in August and September, and it's still visible in post-perihelion images from November, looking remarkably similar to what was seen months earlier. This persistence suggests something more complex than simple perspective effects might be at play. One possibility that researchers are exploring is that the nucleus has an unusual shape and rotation state. If 3I Atlas is highly elongated, shaped more like a potato or a peanut than a sphere, and if it's rotating with its long axis roughly aligned with its direction of travel, active regions at opposite ends could create jets firing in opposite directions. These jets would carry dust and gas away from the nucleus symmetrically, producing the observed pattern. This kind of configuration isn't unprecedented. Several solar system comets have shown evidence of being elongated with active regions at multiple locations. Comet 67P Churyumov-Gerasimenko, visited up close by the European Space Agency's Rosetta mission, turned out to have a distinctive double-lobed structure, like two objects fused together. Its jets fired from specific locations on the surface, creating complex patterns in the coma and tail that varied with the comet's rotation. If 3I Atlas has similar structure, the rotation period becomes crucial. A slowly rotating nucleus would bring different active regions into sunlight over the course of hours or days, creating variability in the jets and the coma. A rapidly spinning nucleus might create more symmetric patterns as the rotation averages out the effects of localized active areas. Without direct imaging of the nucleus itself, astronomers are trying to infer the rotation from variations in brightness and coma structure, but the data so far hasn't yielded a clear answer. Another possibility involves the distribution of volatiles within the nucleus. Comets aren't homogeneous objects. Different layers can have different compositions, perhaps reflecting different epochs in the comet's formation, or different processing it has undergone. If 3I Atlas has volatile-rich regions at specific depths or locations, solar heating penetrating into the interior could drive out gassing from unexpected places. Sunlight doesn't just heat the surface, it penetrates into the outer layers, absorbed by dust grains and warming the material beneath the surface. This subsurface heating can create pressure as ices sublimate, and that pressure has to escape somehow. If the path of least resistance happens to be through cracks or vents that are not directly illuminated, you get jets firing in directions that don't align with the subsolar point, the spot on the surface directly facing the Sun. This process can create extremely complex behavior. Gas building up beneath the surface might erupt suddenly, creating outbursts that temporarily brighten the comet and change the appearance of the coma. Different vents might become active at different times as the rotation brings them to the right orientation, or as subsurface temperatures reach critical thresholds. The result is a comet that's unpredictable, changing in ways that are difficult to model without knowing the internal structure in detail. Some researchers have also suggested that the anti-tail might be related to the comet's possible great age. If 3I Atlas has indeed been wandering through interstellar space for 7 billion years or more, it has been exposed to cosmic radiation for an extraordinarily long time. This radiation can alter the chemistry of surface and near-surface ices, creating compounds that don't exist in younger comets. These altered materials might have different sublimation properties, different optical characteristics, creating behaviors we haven't seen in solar system comets that are only 4.5 billion years old. The James Webb Space Telescope's observations in August might provide clues. JWST's infrared spectrographs can detect specific molecules and measure their abundances with unprecedented precision. If the composition of 3I Atlas shows unusual ratios or unexpected compounds, that could point toward radiation processing or other effects from its long journey through space. The full analysis of JWST's data is still ongoing, and researchers are carefully comparing the spectra to models of cometary composition and radiation chemistry to see if anything stands out as truly anomalous. What makes this investigation challenging is that we don't have baseline data for what an average interstellar comet should look like. With only 3 confirmed examples, and each one different from the others, we can't yet say what's normal and what's unusual for this population. Oumuamua was dry and possibly elongated with unexplained acceleration. Borisov was wet and well-behaved, matching our expectations for comets almost perfectly. 3 Atlas is wet and active, but showing these intriguing structural features that demand explanation. As more interstellar visitors are discovered and studied, we'll start to see whether 3I Atlas's anti-tail is unusual, or whether it's actually common for comets from other star systems. Maybe interstellar comets are generally more likely to have complex structures because of how they're ejected from their home systems. Violent gravitational encounters that fling objects into interstellar space might preferentially select for objects with unusual shapes or compositions. Or maybe we're just seeing natural variation, the same kind of diversity we see in solar system comets, and there's nothing particularly special about 3I Atlas, except that we're paying very close attention to it. The post-perihelion observations will be crucial for answering these questions. As 3I Atlas moves away from the Sun and cools, how will the anti-tail evolve? Will it fade faster than the main tail, suggesting it's driven by a volatile that depletes quickly? Will it persist, indicating a structural feature that doesn't depend on specific temperature conditions? Will it change character, perhaps becoming more or less symmetric as the viewing geometry shifts? Observers around the world are monitoring these changes, capturing images whenever weather and scheduling permit. The Virtual Telescope project, which has been streaming live observations of 3I Atlas, plans to continue following the comet through the winter and into spring. Amateur astronomers with large enough telescopes are contributing their images to databases maintained by organisations like the British Astronomical Association and the American Association of Variable Star Observers. Professional observatories are scheduling follow-up observations at intervals designed to catch any significant changes in the comet's appearance. All of this data will eventually be synthesized into models that attempt to explain the full range of behaviors we've observed. Computer simulations can test different nucleus shapes, different rotation states, different volatile distributions, and see which configurations best match the observations. This kind of modeling has been done successfully for solar system comets observed by spacecraft, where we have ground truth data to validate the models. For interstellar comets, we have to work backward from limited observations, but the fundamental physics is the same, and maybe eventually we'll get lucky. Maybe a future interstellar visitor will be discovered early enough and on a favourable enough trajectory that a spacecraft mission becomes feasible. Imagine getting close-up images of an interstellar comet's nucleus, seeing its shape and surface features directly, watching individual jets erupt and evolve over hours and days. That kind of data would transform our understanding overnight, providing the ground truth we need to interpret what we're seeing in distant observations of objects like 3I Atlas. Until then, we work with what we have: spectra, images, brightness measurements, all analysed with increasing sophistication to extract every bit of information they contain. The anti-tail remains puzzling, a feature that catches the eye and demands explanation, a reminder that even when something looks mostly like what we expect, the details can surprise us and push our understanding forward. But the symmetry in 3I Atlas's case is odd. The main tail and the anti-tail have similar brightness, similar length, as if the comet is spewing material in two opposite directions simultaneously. That would require a symmetric outgassing, jets firing preferentially from specific locations on the rotating nucleus, which in turn would require an irregular surface with concentrated pockets of volatiles. Hubble Space Telescope images from July 21st showed this feature clearly. A teardrop-shaped cocoon of dust coming off the nucleus, elongated in a direction inconsistent, with simple solar wind effects. The Nordic Optical Telescope images from November 11th show it's still there, still pointing toward the Sun, unchanged by perihelion passage. One possibility is that 3I Atlas has a highly elongated shape and is spinning with its long axis roughly aligned with its direction of travel. Active regions at opposite ends of this elongated nucleus could create jets firing in opposite directions, producing the observed symmetry. But that would require very specific geometry and a very specific distribution of volatiles, neither of which is guaranteed. Another possibility is that the anti-tail is actually a perspective effect from dust grains in the orbital plane, but one that's unusually bright and persistent due to the size distribution of the particles. Larger dust grains respond more slowly to radiation pressure and can remain closer to the nucleus longer, creating a more prominent anti-tail than you'd typically see. Or maybe there's something genuinely unusual about 3I Atlas's outgassing pattern, something driven by internal structure or composition that we haven't encountered in solar system comets. Without high-resolution images of the nucleus itself, without spectra detailed enough to map the chemical composition of different regions of the coma, we're largely guessing. But that's part of what makes this so fascinating. Every interstellar object we've detected has been unique, challenging our assumptions about what these cosmic wanderers should look like. Oumuamua was dry and elongated with inexplicable acceleration. Borisov was wet and round and perfectly normal. 3I Atlas is wet and active, but showing structural features that don't quite fit the standard model. Maybe that's just the nature of things when you're sampling objects from completely different planetary systems. Maybe each stellar nursery produces slightly different comets, slightly different asteroids, reflecting the unique conditions in each protoplanetary disk. Or maybe we just don't understand comets as well as we thought we did, and interstellar visitors are teaching us that the diversity of these objects is greater than we realized. For amateur astronomers reading this, here's the practical question. Can you actually see 3I Atlas? The answer is maybe, but it won't be easy, and you'll need the right equipment and conditions. The comet is never going to become bright enough to be visible to the naked eye, not even from the darkest skies on Earth. At current estimates, placing it around magnitude 11 to 12, you'll need a telescope, preferably one with at least an 8-inch aperture and genuinely dark skies free from light pollution. The best viewing opportunity is coming up in mid to late December, when the comet reaches its closest approach to Earth on December 19th. At that point, it will still be about 270 million kilometers away, about 1.8 times farther than Mars at opposition, which gives you a sense of just how distant this object really is. Despite this distance, the geometry will be favourable for Northern Hemisphere observers, with the comet rising in the morning sky around 11 p.m. local time. At closest approach, 3I Atlas will be located in the constellation Leo, not far from Regulus, the constellation's brightest star. Regulus is easy to spot, shining at magnitude 1.4, and it makes an excellent guide star for finding the much fainter comet. If you're using star charts or a planetarium app on your phone, you can plot the comet's position relative to Regulus and use that bright star as an anchor point for your search. But even with good charts and a reasonably large telescope, you're not going to see a spectacular object. Visual observations through the eyepiece will show, at best, a faint fuzzy patch of light, maybe slightly elongated if you're using sufficient magnification and have excellent seeing conditions. You probably won't see colour, you might not see an obvious tail. What you'll see is a soft, diffuse glow that looks very different from the hard points of light that are stars. For most observers, photography will be far more rewarding than visual observation. Long exposure images, even with relatively modest equipment, can reveal details invisible to the human eye. A DSLR camera or dedicated astronomy camera attached to a telescope that can track the stars accurately will allow exposures of several minutes, stack multiple exposures together to reduce noise, and the comet will emerge from the background, showing its coma and possibly even a tail extending away from the nucleus. The key to successful imaging is accurate tracking. Because the comet is moving against the background stars, you need to either track at the star's rate and accept that the comet will trail slightly, or calculate the comet's specific motion and adjust your tracking to follow it, which will make the stars trail instead. Many astronomy software packages can calculate these rates for you if you input the comet's orbital elements. Light pollution is your enemy here. 3i Atlas is faint enough that even moderate light pollution can wash it out completely. If you live in or near a city, you'll need to travel to a dark sky site, somewhere far enough from urban areas that the Milky Way is clearly visible overhead. Dark sky parks, rural locations at high elevation, anywhere the sky background is truly black, will give you the best chance of detecting this elusive visitor. Weather matters too. You need clear skies, obviously, but also stable atmospheric conditions. Turbulence in the atmosphere can blur fine details and make faint objects even harder to detect. Nights with good seeing, when stars appear as steady points rather than twinkling, are ideal for comet observation. Cold winter nights often provide excellent seeing, though you'll need to dress warmly and deal with dew formation on your optics. If you do manage to observe or image 3i Atlas, you'll be looking at something genuinely extraordinary. This isn't a random speck of dust or a distant galaxy. This is an object that formed around a different star, possibly billions of years before Earth existed, that has crossed the vast emptiness between star systems, that is now passing through our solar system for the first and only time. You'll be seeing light reflected from ice that accumulated in an alien protoplanetary disk, photons that have bounced off material that has never felt the sun's warmth until this year. Amateur astronomers have played crucial roles in comet science throughout history, and that tradition continues with interstellar objects. When Borisov was discovered, amateur astronomers around the world contributed thousands of observations that helped professional researchers track its brightness variations, measure its rotation period, and monitor its activity level. The same is true for 3i Atlas. Every observation, every image, every measurement adds to the database and helps astronomers understand this visitor better. If you do capture images of the comet, consider submitting them to organisations like the American Association of Variable Star Observers or the British Astronomical Association, both of which collect and archive comet observations from amateurs worldwide. Your images could end up in scientific papers, contributing to our collective understanding of interstellar objects. But even if you don't have the equipment to observe 3i Atlas yourself, you can follow along as professional astronomers continue to study it. Many observatories post their images online. The Virtual Telescope project regularly streams live observations of interesting objects. Space agencies release data and images from their telescopes. Social media has made astronomy more accessible than ever, with researchers sharing their findings in near real time and explaining what they're seeing. What makes 3i Atlas special isn't its visual appearance, it's what it represents. Direct evidence that water and organic molecules travel between star systems, that the chemistry necessary for life isn't confined to our solar neighbourhood, that the universe is full of these ancient wanderers carrying material from one planetary system to another. That's worth following, even if all you can do is read about it and marvel at the images others capture. The comet will remain observable through winter and into spring 2026, gradually fading as it moves farther from both the Sun and Earth. By summer, it will be too faint for all but the largest amateur telescopes. By the end of the year, it will be receding toward Jupiter, still visible to professional observatories but beyond the reach of most amateur equipment. And then, slowly, inevitably, it will fade into the darkness from which it came, becoming one more faint speck among billions, indistinguishable from background stars heading back, into the interstellar void at over 40 kilometers per second. In 1,000 years, it will have travelled farther from the Sun than any human-made spacecraft has yet reached. In 10,000 years, it will be in the Oort cloud, that vast sphere of icy bodies that marks the Sun's gravitational domain. In 100,000 years, it will have crossed into true interstellar space, no longer influenced by our star's gravity, no longer part of our solar system in any meaningful sense. And someday, maybe in 1,000,000 years, maybe in 1,000,000,000, maybe never, it might encounter another star, another planetary system, another world where astronomers point their telescopes toward the sky and wonder what lies beyond their cosmic shore. And maybe they'll detect it, measure its composition, marvel at the water and organics it carries, and realize, as we have, that the chemistry of life is written into the fabric of the galaxy itself. To truly understand the significance of detecting hydroxyl from 3i Atlas, we need to appreciate how far our observational capabilities have come and where they're heading. The story of astronomy is, in many ways, a story of technological innovation driving scientific discovery. Each new instrument, each improvement in sensitivity or resolution, opens windows on phenomena that were previously invisible. Consider where we were just a century ago. In the 1920s, astronomers were still debating whether spiral nebulae were clouds of gas within our own galaxy or separate island universes millions of light years away. The great debate between Harlow Shapley and Heber Curtis in 1920 reflected genuine uncertainty about the scale and structure of the universe. It wasn't until Edwin Hubble used the 100-inch telescope at Mount Wilson to measure distances to these nebulae that the question was settled. The universe was vastly larger than anyone had imagined. That 100-inch telescope, completed in 1917, was the largest in the world for decades. Its size wasn't arbitrary. Larger mirrors collect more light, allowing astronomers to see fainter, more distant objects. They also provide better resolution, the ability to distinguish fine details. The leap from smaller telescopes to Mount Wilson's giant mirror enabled discoveries that simply weren't possible before, including Hubble's revelation that the universe is expanding, a finding that revolutionized cosmology and led directly to the Big Bang theory. The progression continued through the 20th century. The 200-inch Hale telescope at Palomar, completed in 1948, pushed the boundaries further. Radio telescopes, first developed in the 1930s and 40s, added an entirely new dimension to astronomy. Space telescopes, beginning with early ultraviolet satellites and culminating in Hubble's launch in 1990, eliminated the blurring effects of Earth's atmosphere that limit ground-based observations. Each generation of instruments revealed phenomena their predecessors couldn't detect. Quasars, those incredibly bright objects powered by supermassive black holes, weren't discovered until the 1960s, when radio astronomy had advanced enough to detect them. Pulsars, first found in 1967, required sensitive radio receivers and the realization that some cosmic signals vary on timescales of seconds or milliseconds. Exoplanets, the first of which weren't confirmed until the 1990s, required precise spectrographs capable of detecting the tiny wobble stars make as planets orbit them. Now we're in another golden age of astronomical instrumentation. The James Webb Space Telescope, launched in December 2021, observes the universe in infrared wavelengths with sensitivity far exceeding any previous instrument. Its discoveries in just its first few years of operation have included the earliest galaxies ever seen, detailed atmospheres of exoplanets, and stunning views of star formation in dusty nebulae. JWST's observations of 3i Atlas in August 2025 added crucial data about the comet's composition that complemented the radio detection from MeerKAT. The Vera C. Rubin Observatory, completing commissioning now in late 2025, represents another leap forward. Its 8.4-metre primary mirror isn't the largest in the world, far from it. But its wide field of view and massive digital camera, the largest ever built for astronomy, allow it to photograph huge swaths of sky in single exposures. Over its 10-year legacy survey of space and time, Rubin will create a movie of the universe, capturing everything that moves or changes brightness. For interstellar object science, Rubin is transformative. Current surveys like Atlas and Pan-STARRS, excellent as they are, cover relatively limited areas of sky on any given night. They catch interstellar visitors, but often only weeks or months before perihelion. Rubin will see them earlier, when they're still faint and far out, giving astronomers precious extra time to plan observations. Estimates suggest Rubin could discover dozens of interstellar objects per year, maybe more, building up a statistical sample that will reveal patterns invisible in our current handful of detections. The Square Kilometre Array, or SKA, under construction in South Africa and Australia, will revolutionise radio astronomy just as dramatically. When completed, SKA will have collecting area measured in square kilometres, as the name suggests, spread across thousands of antennas, its sensitivity will dwarf current instruments, including MeerKAT, which is actually a precursor and pathfinder for SKA. If MeerKAT can detect hydroxyl from an interstellar comet at 1.4 AU from the Sun, SK will be able to detect it from much greater distances, tracking the onset of activity from far beyond Mars's orbit. SK will also detect many more molecular species. Hydroxyl is relatively easy to detect because it's abundant and has strong spectral lines. But comets contain dozens of other molecules, each with its own characteristic radiosignature: carbon monoxide, formaldehyde, methanol, hydrogen cyanide, even complex organics like ethanol and glycolaldehyde, a simple sugar, have all been detected in solar system comets using radiospectroscopy. SKA will measure all of these in interstellar comets, building up complete chemical inventories that reveal how compositions vary from object to object and what that variation tells us about their origins. Ground-based optical astronomy is advancing too. The extremely large telescope under construction in Chile with a 39-meter primary mirror will be the largest optical telescope in the world when it's completed. The Giant Magellan Telescope, using 7 8-meter mirrors working together, will provide both collecting area and resolution that current telescopes can't match. These giants will be able to study faint, distant objects with unprecedented detail, potentially even resolving the nuclei of interstellar comets when they're close enough, seeing the actual solid bodies rather than just the fuzzy comas that surround them. Adaptive optics, systems that use deformable mirrors to correct for atmospheric turbulence in real time, continue to improve. The latest systems can produce images from ground-based telescopes that rival or exceed Hubble's resolution, at least for bright objects in favourable conditions. For studying comets, where you want to see both the faint, extended coma and the brighter nucleus, adaptive optics can provide views that were simply impossible a generation ago. And then there are the interferometers, instruments that combine light or radio waves from multiple telescopes separated by large distances. The Event Horizon Telescope, which produced the first image of a black hole's shadow, uses radio dishes spread across the entire Earth, creating an effective aperture the size of the planet. Similar techniques applied to studying interstellar objects could potentially resolve features on their nuclei, seeing individual jets or active regions, mapping the distribution of different ices across their surfaces. All of these technologies working together will transform our understanding of interstellar visitors over the coming decades. We'll go from having 3 confirmed objects with limited data to having hundreds with comprehensive measurements across the electromagnetic spectrum. We'll be able to classify them, sort them into categories based on their properties, trace their likely origins, understand the relationship between their compositions and the types of stars they formed around. We'll also, almost certainly, find surprises, objects that don't fit our categories, compositions we didn't expect, behaviours that challenge our models. That's how science advances, through the interplay between prediction and observation, between what we think should happen and what actually does. Every surprise is an opportunity to learn something new, to refine our theories, to discover phenomena we hadn't anticipated. The detection of hydroxyl from Thruway Atlas is a beginning, not an end. It's the first chapter in what will become a rich literature of interstellar object spectroscopy. 20 years from now, astronomers will look back on this detection, the way we now look back on early exoplanet discoveries, as the pioneering work that opened a new field. Textbooks will mention it as the first radio detection of an interstellar object, a milestone in the history of astronomy. But the real significance isn't in the first label. It's in what this detection represents about our growing ability to study the galaxy beyond our immediate neighbourhood. We're no longer limited to observing stars and galaxies, objects so distant or so bright that they're relatively easy to detect. We can now probe the chemistry of small, faint objects passing through our solar system, measuring molecules from material that formed around other stars. We're reading the galaxy's chemical composition one interstellar visitor at a time, building a map of where different elements and compounds exist, how they're distributed, what that tells us about stellar and planetary evolution. That's the true power of modern astronomy. Not just seeing further or with better resolution, but understanding what we're seeing, extracting information from every photon, every radio wave, every gravitational wave. The universe is broadcasting its story constantly, in every wavelength at every scale, and we're finally developing the instruments and the knowledge to listen effectively, to translate that cosmic broadcast into understanding. The hydroxyl signal from 3i Atlas is just one word in that vast cosmic story, but it's a word we couldn't have read even a decade ago, and it points toward chapters we're only beginning to comprehend. Behind every great astronomical discovery are people, the scientists and engineers and technicians who build the instruments, plan the observations, analyse the data, and interpret the results. The hydroxyl detection from 3i Atlas involved teams spanning continents, dozens of individuals contributing their expertise to make this measurement possible. Their story deserves telling because it illuminates how modern astronomy actually works. As a collaborative enterprise requiring diverse skills and perspectives, radio astronomy is particularly collaborative by necessity. Operating a facility like MeerKAT requires specialists in multiple domains. Engineers maintain the dishes, ensuring their surfaces remain precisely shaped and their pointing is accurate to fractions of a degree. Receiver experts keep the sensitive electronics working, dealing with the challenge of amplifying signals that are barely distinguishable from background noise. Software engineers write and maintain the correlator code that combines signals from 64 dishes in real time, a computational challenge that requires processing terabytes of data per day. And astronomers plan the observations, interpret the data, write the papers that communicate results to the scientific community and the public. For the 3i Atlas observations, planning began months before October. Astronomers had to make the case for why observing this object with MeerKAT was scientifically valuable. They had to convince time allocation committees, the groups of scientists who decide which projects get telescope time, that the potential rewards justified the risk. Remember, the September observations found nothing. Those negative results could have been interpreted as showing the technique didn't work, that hydroxyl from an interstellar comet was too faint to detect. But the astronomers understood that timing mattered, that the comet wasn't producing enough hydroxyl yet, and they persisted, requesting additional observations for October when conditions should be better. That persistence paid off. The October 24th observation succeeded where the September attempts had not, vindicating the planning and the patience. But success required more than just pointing the telescope in the right direction. The data that came back from MeerKAT was raw, filled with noise and systematic effects that had to be carefully removed. Radio frequency interference from satellites and terrestrial sources had to be identified and filtered out. Calibration errors had to be corrected. Only after all this processing did the hydroxyl lines emerge clearly from the background. Interpreting those lines required understanding cometary chemistry, knowing what hydroxyl abundances to expect for a comet at that distance and temperature, calculating the Doppler shifts based on the comet's velocity, checking that everything made physical sense. This is where the collaboration with other observers became crucial. The swift ultraviolet observations provided independent confirmation of water production. JWST's infrared measurements gave information about temperature and other volatiles. Ground-based optical images tracked the comet's brightness and tail morphology. All of these datasets, collected by different teams using different instruments, had to be synthesized into a coherent picture of what 3i Atlas was doing as it approached perihelion. The human element also includes the competition and collaboration that drives science forward. When an interesting object like 3i Atlas appears, multiple teams want to observe it. There's competition for telescope time, for being first to publish certain results, for having your work cited by others in the field. This competition can be intense, sometimes leading to tensions, but it also motivates astronomers to do their best work, to be thorough and careful, because they know others are checking their results. At the same time, there's extraordinary collaboration. Data is shared, sometimes before formal publication. Astronomers coordinate observations to avoid duplication and ensure comprehensive coverage. When someone makes a discovery, even competitors will often congratulate them and look for ways to build on or complement the work. The culture of astronomy balances competition with cooperation in ways that generally serve the science well, pushing the field forward through both rivalry and mutual support. The public communication of discoveries like this one also requires skill and care. When the hydroxyl detection was announced, astronomers had to explain why it mattered to audiences ranging from fellow scientists to journalists to the general public. Each audience requires different language, different levels of detail, different framing. Scientists want to know the technical details, the signal-to-noise ratios, the line widths, the implications for models. Journalists want a story, an angle, something that will engage their readers. The public wants to understand the basic discovery and why they should care. Navigating these different audiences while maintaining scientific accuracy is challenging. This is where controversies like Avi Loeb's suggestions about artificial origins become particularly delicate. From a public engagement standpoint, the "could it be aliens" angle generates enormous interest. People who would never read a paper about hydroxyl spectroscopy will click on an article suggesting an interstellar visitor might be artificial. But from a scientific accuracy standpoint, that angle can be misleading, suggesting mysteries where mainstream science sees straightforward explanations. The astronomers who made the hydroxyl detection had to balance these concerns. They wanted to communicate the genuine significance of the discovery, the first radio signal from an interstellar object, without overselling it or allowing speculation to overshadow the solid science. They had to acknowledge the coincidence with the WOW signal region, while making clear it was almost certainly just coincidence. They had to explain why the detection was important for understanding interstellar chemistry, while not claiming more than the data actually showed. This communication challenge is part of modern astronomy. In an era of social media and instant news cycles, discoveries are shared and discussed globally within hours. Misinterpretations can spread faster than corrections. The pressure to have clear, accurate, accessible explanations ready quickly is intense. And yet the scientists doing this communication are the same people doing the observations and analysis, adding media relations to their already substantial workload. The success of the 3i Atlas hydroxyl detection, then, isn't just about the technology or the timing, it's about the people who made it happen. The astronomers who planned the observations and fought for telescope time, the engineers who kept MeerKAT running at peak performance, the data analysts who extracted signal from noise, the theorists who provided context and interpretation, the communicators who explained the results to wider audiences. Modern astronomy is a team sport, and this detection showcases what dedicated teams can accomplish when everything comes together. For all that the hydroxyl detection tells us, there's far more we still don't know about 3i Atlas. This is true of virtually every astronomical discovery. Each answer raises new questions. Each measurement reveals how much remains to be measured. Let's explore what the current observations leave uncertain and what future work might reveal. First, we still don't know exactly how big 3i Atlas is. Observations from Hubble Space Telescope place upper limits on the nucleus size at around 5.6 kilometers in diameter, but the lower limit is much smaller, potentially as little as 440 meters. That's a factor of more than 10 uncertainty in size, which translates to enormous uncertainty in mass and composition. A 5-kilometer nucleus would have vastly more ice than a half-kilometer one, implying different formation conditions and evolutionary history. The size matters for understanding the object's origin. Smaller bodies are more easily ejected from their parent systems. A close encounter with a giant planet could fling a small comet into interstellar space with relatively modest gravitational assists. Larger bodies require either more dramatic ejection events or formation in regions where high-velocity ejection is common. If we could pin down the size precisely, it would constrain models of how interstellar objects get launched from their birth systems. We also don't know the rotation state with certainty. The brightness variations suggest the nucleus is rotating, but we can't tell if it's simple rotation around a single axis or complex tumbling. The rotation period appears to be somewhere between 8 and 12 hours, based on how the brightness changes, but those estimates come with large uncertainties. High-resolution images showing how the coma structure changes with time could reveal the rotation more precisely, but such images require either very large telescopes or spacecraft close-ups, neither of which are currently available for 3i Atlas. The internal structure remains a complete mystery. Is the nucleus a single solid body, perhaps like a flying mountain held together by its own gravity? Or is it a loosely bound rubble pile, a collection of smaller fragments held together by ice acting as cement? The distinction matters for understanding how these objects form and evolve. Rubble pile structures would have very different thermal properties than solid bodies, affecting how heat propagates into the interior and where outgassing occurs. The detailed composition is still uncertain. We know there's water because we detected hydroxyl. We know there's likely carbon dioxide from JWST's infrared observations. But what about the ratios? How much water compared to CO2 compared to other volatiles? What's the dust-to-gas ratio? What kinds of organic molecules are present? These details would tell us about the temperature and pressure conditions in the protoplanetary disk where 3I Atlas formed, about how similar or different that disk was from the one that produced our solar system. Isotopic ratios would be particularly valuable. The ratio of deuterium to hydrogen in water reveals temperature conditions during formation. The ratio of different oxygen isotopes similarly constrains formation conditions. Carbon isotopes tell stories about where the carbon came from, whether it formed in the protoplanetary disk or was inherited from the interstellar medium that the disk collapsed from. But measuring isotopes in such a faint, distant object is beyond current capabilities. We'd need either much more sensitive instruments or a spacecraft encounter that could measure isotopes directly. The long-term history of the object is speculative. We can estimate it's probably billions of years old based on stellar dynamics, but we don't know how many times it might have encountered other stars during its interstellar wandering. Each close pass by a star would have warmed the object, potentially driving off volatiles and altering its composition. An object that's been wandering for 7 billion years and never came close to another star would be very different from one that's had multiple stellar encounters. The immediate future trajectory is predictable, computed from the current orbit. But tiny forces, like the non-gravitational acceleration from asymmetric outgassing, can accumulate over time, making long-term predictions uncertain. Where will 3I Atlas be in 1 million years? Probably we can calculate that reasonably well. But in 10 million years, 100 million? The cumulative effects of small perturbations, encounters with molecular clouds, gravitational interactions with stars it passes, all of these could change the trajectory in ways we can't currently predict. And of course, the big question remains unanswered, and likely unanswerable with current data. Is there anything at all unusual about 3I Atlas beyond it being an interstellar visitor? The anomalies, the anti-tail and brightness variations and post-perihelion activity can all be explained by natural processes with some reasonable assumptions about internal structure and composition. But are those assumptions correct? Or is there something genuinely different about this object that we're missing because we don't have the right observations? This uncertainty is both frustrating and exciting. Frustrating because we want definitive answers, clear explanations, closure on the mysteries. But exciting because uncertainty means opportunity. Every unanswered question is an invitation to future observations, to better instruments, to new approaches, the unknowns. About 3 Atlas will motivate proposals for the next generation of telescopes. They'll drive mission concepts for spacecraft that can catch these visitors. They'll inspire theoretical work modelling how interstellar objects form and evolve. Science thrives on the unknown. If we understood everything about 3 Atlas completely, if there were no mysteries left, it would still be interesting as the first interstellar object to produce a radio detection. But the scientific value would be limited. The gaps in our knowledge, the measurements we couldn't make, the questions we can't yet answer, these are what make the story ongoing. This isn't the end. It's barely the beginning of understanding what interstellar visitors can teach us about the galaxy. We need to address the speculation that's been swirling around 3I Atlas since its discovery, particularly the suggestions from Harvard astronomer Avi Loeb that this object might be something more than a natural comet. Loeb has been the most prominent voice raising the possibility that 3I Atlas could be artificial, a probe sent by an extraterrestrial intelligence. In essays and blog posts, Loeb has questioned whether the comet's brightness might stem from self-luminosity rather than reflected sunlight, a property unlike any known comet. He's noted the unusual features, the anti-tail, the brightness variations, the coincidental proximity to the WOW signal region. In one provocatively titled paper, Is the Interstellar Object 3I Atlas Alien Technology?, Loeb laid out the hypothesis explicitly and explored its implications. The hypothesis in question is that the recent interstellar visitor to our solar system, 3I Atlas, is a technological artifact and furthermore has active intelligence, Loeb wrote. If this is the case, then 2 possibilities follow. First, that its intentions are entirely benign, and second, they are malign, or somewhere in between. The consequences, should the hypothesis turn out to be correct, could potentially be dire for humanity and would possibly require defensive measures. NASA and mainstream astronomers have responded to this speculation with measured clarity. It looks like a comet. It acts like a comet. All our observations are consistent with a natural object. agency officials and researchers stated in response to questions about the speculation. There's no evidence of artificial origin, no anomalous properties that can't be explained by standard cometary physics. The scientific community has largely agreed with NASA's assessment. The hydroxyl detection from MeerKAT is perfectly consistent with natural water outgassing. The brightness variations, while unusual, aren't outside the range of what solar system comets display. The anti-tail can be explained by perspective effects and dust grain dynamics. The coincidence with the WOW signal region is just that, a coincidence. But Loeb makes an interesting point that's worth considering, even if you disagree. With his conclusions, he argues that we should at least examine the possibility of artificial origin for interstellar objects, that dismissing it out of hand without investigation is itself unscientific. We should be open-minded but rigorous, Loeb has said in interviews. We should follow the evidence wherever it leads, even if that makes us uncomfortable. Loeb has developed what he calls the Loeb scale, ranking interstellar objects from 0 for definitely natural to 10 for definitely technological. By his assessment, 3i Atlas ranks at 4 due to what he describes as 8 documented anomalies, though many scientists in the field don't use this framework and maintain that all observed features can be explained naturally. The challenge is that extraordinary claims require extraordinary evidence, and so far 3i Atlas displays no characteristics that demand an artificial explanation. Occam's razor, the principle that the simplest explanation is usually correct, strongly favours the natural comet hypothesis. A technological artifact would need to perfectly mimic natural cometary behaviour, which is possible but adds layers of unnecessary complexity to the explanation. Still, Loeb's advocacy has done something important. It's kept people interested in 3i Atlas, kept it in the public consciousness, kept funding flowing for observations that might otherwise have been deprioritised. Even if the object turns out to be nothing more than an ordinary comet from another star system, the data we're collecting will be invaluable for understanding how these objects form and evolve. And who knows? Maybe decades from now, when we have the technology to send probes to intercept interstellar visitors, when we can analyse their composition up close with instruments far more sophisticated than anything we have today, maybe we'll discover something we didn't expect. Maybe the line between natural and artificial is blurrier than we currently think. Maybe intelligence can emerge in forms so alien to our experience that we wouldn't recognise it even if we were looking right at it. Or maybe 3i Atlas is just a comet, and that's extraordinary enough. Let's zoom out and consider what the hydroxyl detection from 3i Atlas means in the broader context of astrobiology and the search for life beyond Earth. Water is the universal solvent, the liquid that made biology possible on our planet. Every drop of water in your body, every molecule that makes up roughly 70% of you, is the same H2O that exists throughout the universe. The detection of water, or its signature in hydroxyl radicals, from an interstellar comet proves something fundamental. The ingredients for life aren't unique to Earth, or even to our solar system. They're common, distributed throughout the galaxy on countless icy bodies, ejected from their home systems during planetary formation. This supports what's called the panspermia hypothesis in its most conservative form, not the radical idea that living organisms travel between stars, which most scientists find implausible given the harsh conditions of interstellar space, but the more measured suggestion that life's chemical precursors, the building blocks necessary for biology to emerge, are mobile on cosmic timescales. Think about it this way. Every planetary system probably ejects millions or billions of comets and asteroids during its formation, flinging them into interstellar space through gravitational interactions with giant planets. Those objects carry with them samples of the protoplanetary disk material, including water ice, carbon dioxide, methane, ammonia, and complex organic molecules. They drift through the galaxy for millions of years, occasionally encountering other star systems. When they do, when gravity captures them, or at least bends their trajectories inward, they can deliver their cargo of volatiles and organics to young planets that might be at just the right temperature and pressure for liquid water to exist on their surfaces. Earth almost certainly received at least some of its water and organics this way. The debate is over how much. Some models suggest that Earth formed relatively dry and acquired most of its water through late-stage impacts from comets and asteroids. Other models suggest that water was present from the beginning, incorporated into the rocky material that assembled to form our planet. But regardless of the details, the broader picture is clear. Water and organic molecules move around the galaxy. They don't stay locked in individual stellar systems. They spread, they mix, they redistribute through a process that operates on timescales of billions of years, but touches every corner of the Milky Way. If Earth could receive water and organics from interstellar visitors, so could every other potentially habitable planet. That means the chemistry necessary for life as we know it is probably widespread, available on countless worlds, seeded by the same galactic-scale delivery system that 3I Atlas is part of. The question then becomes, if the ingredients are common, why does life seem rare? Or is it rare? We've only explored one planet in detail. We've found no definitive evidence for life anywhere else in the solar system, though investigations of Mars and Europa and Enceladus continue. We've detected no technosignatures, no unambiguous signs of technological civilizations, despite decades of CT observations. Maybe the step from chemistry to biology, that transition from complex organic molecules to self-replicating systems capable of evolution, is vanishingly unlikely. A statistical fluke that's happened only once in the observable universe. Or maybe it's common, but life rarely evolves intelligence. Or maybe intelligence is common, but technological civilizations destroy themselves or transcend into forms we can't detect. Or maybe we're just not looking in the right way, with the right instruments, asking the right questions. Maybe the universe is full of life and we simply don't know how to recognize it yet. 3I Atlas doesn't answer these questions, but it provides one crucial data point. The chemistry is out there, mobile and widespread, written into the fabric of the galaxy itself. The detection of hydroxyl from 3I Atlas marks a turning point in how we study interstellar visitors. Before this, we relied primarily on optical and infrared observations, analysing reflected sunlight and thermal emissions to infer composition and structure. Radio detections were considered unlikely, not something you'd routinely attempt. But now, we know it's possible. Now we know that radio telescopes like MeerKAT can detect molecular signatures from these objects when the geometry and timing align. That opens up entirely new avenues for investigation. The next interstellar visitor might be even richer in volatiles, producing stronger hydroxyl signals that can be detected earlier in its passage through the solar system. It might have different molecular abundances, giving us insight into how chemical composition varies between planetary systems. It might show unexpected spectral features, hinting at exotic ices that don't exist in our solar system. We're entering an era where interstellar object science is transitioning from opportunistic observations of chance discoveries to systematic campaigns using networks of instruments spanning the electromagnetic spectrum. When the Vera C. Rubin Observatory comes fully online, its legacy survey of space and time will discover dozens of interstellar objects per year, catching them months before they reach perihelion and giving astronomers time to coordinate observations. Radio telescopes, optical telescopes, infrared instruments, ultraviolet satellites, all working together to build complete pictures of these cosmic wanderers, spectroscopy to measure composition, photometry to track brightness variations, polarimetry to study dust grain properties, high-resolution imaging to resolve structures in the coma and tail, and eventually spacecraft missions. The European Space Agency's Comet Interceptor mission, currently under development, is designed to wait at a gravitationally stable point in space until a suitable target appears, then race to intercept it with instruments capable of in-situ measurements. Imagine flying through the coma of an interstellar comet, sampling its composition directly with mass spectrometers, imaging its nucleus from kilometers away with high-resolution cameras. That's the future we're building toward. A future where interstellar visitors aren't mysterious anomalies, but routine subjects of scientific investigation. Where we catalogue their compositions, track their orbits, understand their origins well enough to identify which stellar systems they likely came from based on their trajectories and chemical signatures. 3's Atlas is showing us the way. It's demonstrating what's possible when you combine sensitive instruments with careful planning and good timing. It's proving that these ancient travellers from distant star systems can tell us their stories if we know how to listen. As of mid-November 2025, 3I Atlas is receding from the Sun, climbing back out of the inner solar system on its way toward a close encounter with Jupiter in March 2026. The comet is still active, still producing gas and dust, still brightening the morning sky for observers with telescopes large enough to detect it. The December 19th closest approach to Earth will be the last really good opportunity to study it from our planet. After that, it will fade rapidly as it moves farther away, eventually becoming too dim for all but the largest telescopes to detect. By mid-2026 it will be gone, a faint speck receding into the darkness, travelling at over 40 kilometers per second toward a rendezvous with interstellar space that no one alive today will ever witness. The data we've collected, the spectra and images and measurements spanning months of observation, will keep astronomers busy for years. Every spectrum needs to be analysed in detail. Every brightness variation needs to be explained. Every anomaly needs to be investigated. The goal is to build a complete model of 3i Atlas, to understand not just what it is but where it came from, how it evolved, what it tells us about planetary system formation beyond our solar system, and we'll be watching for the next one. Because 3i Atlas won't be the last interstellar visitor. It's just the third we've confirmed, but simulations suggest that at any given moment, dozens of these objects might be passing through the inner solar system, most of them too faint and too fast for current surveys to detect. As our instruments improve, as our survey telescopes cover more sky more often, the discovery rate will increase. In 10 years, 20 years, we might have confirmed hundreds of interstellar objects. We'll start to see patterns in their compositions, their orbits, their physical properties. We'll be able to say things like, objects from this region of the galaxy tend to have this carbon-to-oxygen ratio, or comets ejected from stellar systems with this type of planetary architecture show this type of volatile abundance. We'll map the chemical diversity of the galaxy, not by sending probes to thousands of star systems, which is impossible with current or foreseeable technology, but by studying the samples that come to us, the interstellar objects that wander through our neighbourhood every year or two. And maybe, just maybe, one of them will show something genuinely anomalous, something that doesn't fit natural explanations no matter how hard we try to force the data into conventional models, a trajectory too perfect to be coincidence, a composition too regular to be random, a signal too structured to be noise. That day hasn't come yet. 3i Atlas, for all its mysteries, for all its unusual features, is almost certainly a natural object, a comet doing comet things, distinguished mainly by the fact that it formed around another star. But the fact that we're now capable of detecting and studying these visitors in such detail means we'll be ready when something truly unprecedented passes through. We're building the infrastructure, developing the techniques, training the algorithms, coordinating the telescopes. We're learning the language of interstellar chemistry, one spectrum at a time, one detection at a time, one visitor at a time. There's something poetic about the fact that the first radio signal we've ever detected from an interstellar object was hydroxyl, water's breakdown product, the chemical fingerprint of H2O. Water is so fundamental to everything we know about life, so essential to Earth's habitability, that finding it on an object from another star system feels significant in a way that transcends the pure science. It's a reminder that we're not isolated, that the chemistry that made our world habitable exists elsewhere, operates by the same rules everywhere, produces the same molecules throughout the cosmos. The universe, for all its vastness and apparent emptiness, is fundamentally interconnected. Material moves between stars. Information, encoded in chemical composition and isotopic ratios, travels across light years on wandering icebergs like 3i Atlas. The message those molecules carry is simple but profound. You're not alone. Not in the sense of intelligence or communication, but in the deeper sense that the building blocks of life are everywhere. That water exists throughout the galaxy. That organic compounds form spontaneously in protoplanetary disks around every star. That the raw materials for biology are written into the structure of the universe itself. Maybe that's the real significance of detecting hydroxyl from 3i Atlas. Not that it proves anything about alien civilizations or technological artifacts, but that it demonstrates, in the clearest possible terms, that life's chemistry is universal. That wherever liquid water exists in contact with organic molecules and an energy source, the same kinds of chemical reactions occur. The same amino acids form, the same nucleobases assemble, the same phospholipids create membranes. The cosmos has been broadcasting this message for billions of years, written in molecular absorption lines and emission features, transmitted across the electromagnetic spectrum for anyone with the instruments and knowledge to read it. 3i Atlas brought that message to our doorstep, close enough to study in unprecedented detail, loud enough to hear for the first time. If you've made it this far through this late-night exploration of 3i Atlas and its historic radio detection, thank you for staying with me. This is a story that's still unfolding, a discovery whose full implications might not be clear for years or decades. But it represents something important, a milestone in humanity's expanding ability to read the messages the universe has been sending all along. We started this journey in the Karoo Desert on October 24th, with MeerKAT detecting 2 faint absorption lines from a visitor from another star system. We've explored the science of hydroxyl radicals, the mystery of the WOW signal connection, the implications for life's origins, and the future of interstellar object science. We've learned that based on trajectory analysis and models of stellar evolution, 3i Atlas could be at least 7 billion years old, potentially making it twice as ancient as Earth itself. Though these estimates come with significant uncertainty, that it contains water and organic molecules identical to those in our own solar system's comets, that it survived perihelion intact and is now climbing back into the morning sky, visible to anyone with a large enough telescope and the dedication to find it. We've grappled with speculation about artificial origins while acknowledging that extraordinary claims require extraordinary evidence, and the evidence overwhelmingly supports a natural explanation. We've seen how coincidences can spark imagination even when they're probably meaningless. And we've glimpsed a future where interstellar visitors are routine subjects of scientific study, rather than once-per-decade sensations. But more than anything, we've witnessed a moment of genuine discovery. The first time humanity has detected a radio signal from an object born around another star. The first time we've directly measured the chemistry of interstellar material using radio spectroscopy. A milestone that will be remembered when astronomers look back at this era, decades or centuries from now, trying to understand when and how we learned to read the chemical messages written across the galaxy. 3i Atlas is already more than 300 million kilometers from Earth and getting farther every second. By this time next year it will have passed Jupiter and be heading for the outer solar system, its brief encounter with our Sun fading into memory. In a century, it will have crossed beyond the orbit of Neptune, entering the vast emptiness of the Kuiper Belt, and then the Oort cloud, that spherical shell of icy bodies that marks the fuzzy boundary between what belongs to our solar system and what doesn't. In 1 million years, maybe 2, it will cross into true interstellar space, joining the trillions of other wanderers drifting between the stars, carrying with it whatever memories frozen into its ancient ice, whatever stories written in isotopic ratios and molecular abundances. And maybe, billions of years from now, it will encounter another star system, fall into another sun's gravity well, warm once more under alien sunlight, and speak to another civilization in that same language of chemistry and light. The hydroxyl detection from 3i Atlas represents more than just a single successful observation. It marks the beginning of a new era in how we study objects from beyond our solar system. Think about what we've accomplished in less than a decade. The first interstellar object, 1Iai Oumuamua, was discovered in 2017, and we barely managed to get a handful of observations before it sped away into the darkness. We learned it was unusual, but we couldn't pin down exactly what it was or where it came from. The second object, 2I Borisov in 2019, gave us more time and better data. We determined it was a comet, measured its composition, tracked its behavior. But we were still relying almost entirely on optical and infrared observations, traditional techniques that have been used for centuries to study celestial objects. Now, with 3i Atlas, we've added radio spectroscopy to our toolkit. We've shown that we can detect specific molecules in these interstellar visitors, that we can measure their abundances and temperatures, that we can track how their chemistry evolves as they approach and leave the Sun. This is a fundamentally more powerful way to study these objects than what was possible just a few years ago, and the technology is only getting better. The MeerKAT telescope that made this detection is part of a larger project called the Square Kilometre Array, or SKA, which when completed will be the most powerful radio telescope ever built. SKA will have collecting area measured in square kilometres, spread across sites in South Africa and Australia, with sensitivity that dwarfs even MeerKAT's impressive capabilities. When SKA comes online in the coming years, it will be able to detect hydroxyl and other molecules from interstellar objects even when they're much farther from the Sun, much fainter, much more difficult to observe. It might even be able to detect molecules we've never seen in comets before, exotic ices that only exist in certain types of planetary systems, or organic compounds that form under conditions different from those in our solar system. The James Webb Space Telescope continues to revolutionize infrared astronomy, mapping temperatures and detecting gases with unprecedented precision. Its observations of 3I Atlas in August provided our first detailed look at the comet's infrared spectrum, revealing information about carbon dioxide and other volatiles that complement the water measurements from Swift and MeerKAT. JWST can observe dozens of interstellar objects over its planned operational lifetime, building up a catalogue of compositions and properties that will reveal patterns we can't see with just 3 data points. Maybe objects from certain regions of the galaxy have higher carbon-to-oxygen ratios. Maybe comets ejected from systems with hot Jupiters have different volatile abundances than those from systems with cold, distant giant planets. We won't know until we measure enough of them to see the statistical trends. The Vera C. Rubin Observatory, currently completing its final testing before beginning full science operations, will transform our ability to discover these visitors in the first place. Rubin's massive camera and wide field of view will scan the entire visible sky every few nights, creating a time-lapse movie of the universe that captures everything that moves or changes brightness. Current estimates suggest Rubin will discover dozens of interstellar objects per year, maybe more, catching them months before they reach perihelion and giving astronomers time to coordinate observations across the full range of instruments available. Imagine what we could do with that kind of advance warning. Instead of scrambling to observe an object that was discovered just weeks before perihelion, we could plan comprehensive campaigns spanning months or even years. Radio telescopes could monitor the onset of volatile activity. Space telescopes could track how the coma develops. Ground-based spectrographs could measure composition at multiple epochs. Spacecraft, if mission planners were really ambitious and lucky with timing, could be redirected for flybys. The European Space Agency's Comet Interceptor mission, scheduled for launch in the late 2020s, is designed explicitly for this kind of rapid response. The spacecraft will park itself at a gravitationally stable point in space called Lagrange Point 2, about 1.5 million kilometers from Earth in the direction away from the Sun. There it will wait, its instruments powered down, its trajectory stable without needing fuel, until an appropriate target appears. When an interstellar comet is discovered heading into the inner solar system, Comet Interceptor can be activated and sent on an intercept course. The mission consists of 3 separate spacecraft that will fly through the comet's coma from different angles, taking measurements, capturing images, analysing dust and gas composition in situ. For the first time, we'll have direct samples of interstellar material, not filtered through Earth's atmosphere, not limited by what our ground-based telescopes can see, but measured directly by instruments flying through the comet itself. The data from such a mission would be extraordinary. We could measure isotopic ratios that reveal where in the galaxy the comet formed. We could detect organic molecules too complex or too rare to show up in ground-based spectra. We could image the nucleus at resolutions high enough to see individual features, boulders and cliffs and jets of gas erupting from specific locations. We could measure magnetic fields and plasma environments, dust grain sizes and compositions, everything that makes these objects what they are. But even without spacecraft visits, the ground-based and space-based observations we're conducting now are revealing the galaxy's chemical diversity. Every spectrum we capture, every measurement we make, adds to our understanding of how planetary systems form and evolve, how comets accumulate their ice and organics, how material gets redistributed through gravitational interactions. The ratios of different isotopes, different versions of the same element with different numbers of neutrons, can tell us about the temperature and pressure conditions when the ice formed. The abundances of various molecules reveal which volatiles were present in the protoplanetary disk, and in what proportions. The dust-to-gas ratio indicates how much solid material got incorporated versus how much remained as gas. All of this information, extracted from light and radio waves that have travelled hundreds of millions of kilometers to reach our instruments, paints a picture of worlds we'll never visit, stars we can barely see, planetary systems that might not even exist anymore. And with each new visitor, with each new spectrum and measurement and observation, that picture becomes clearer. We're learning that the chemistry of life is truly universal, that water and organics exist throughout the galaxy, that the building blocks necessary for biology aren't special or rare but common and mobile. We're learning that comets from other star systems look remarkably like comets from our own, suggesting that the processes that form these objects operate the same way regardless of where they happen. But we're also finding hints of diversity, subtle differences in composition and behaviour that reflect the unique conditions in each planetary system. Some interstellar objects might be richer in carbon compounds, others might have more water, some might contain molecules we've never detected before, chemical signatures of formation environments very different from our own solar system's history. The hydroxyl detection from 3i Atlas is a milestone in this ongoing exploration. It's not the end of the story, but rather a new chapter, one where we can directly probe the molecular makeup of objects from beyond our solar system. It's a chapter where radio spectroscopy joins optical astronomy and infrared observations as essential tools for understanding these cosmic visitors. And it's a chapter where every new detection brings us closer to answering fundamental questions about our place in the universe. Do other planetary systems produce the same kinds of comets as ours? Are the ratios of water to carbon dioxide to carbon monoxide universal, or do they vary significantly? What can those variations tell us about the temperatures and pressures in different protoplanetary disks? Can we use chemical signatures to infer properties of the stars around which these objects formed, even if we can't identify those specific stars? These questions, once purely theoretical, are now becoming empirical. We're not just speculating about what interstellar objects might be like. We're measuring them, analysing them, building databases of their properties, and as that database grows, as we transition from 3 confirmed objects to dozens to hundreds, patterns will emerge that reveal the underlying physics and chemistry of planetary system formation throughout the galaxy. But for a few months in late 2025, it was ours to study. And it told us something worth remembering. The universe is full of chemistry, full of information, full of stories waiting to be read by anyone who knows how to listen. The cosmos has been whispering all along. We're only now learning its language. If these developments have you hooked the way they have me, make sure to hit that like button and subscribe so you don't miss future updates as this story continues to unfold. Drop a comment with where you're tuning in from and what you think about this historic detection. Your engagement keeps stories like this one coming. Until next time, keep looking up. The next interstellar visitor is already out there somewhere, and it might arrive sooner than we think.